No?
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Julia? Okay, it's 9 o'clock, so it's time to start. I would like to ask Professor Vitaly Ivanov, General Chair of the conference, to take the floor.
Good morning, dear participants, dear ladies and gentlemen. It is a great honor for me to start the 5th International Conference on Design, Simulation, Manufacturing, the Innovation Exchange. I am happily welcoming all of you from the conference room at Sumy State University. The presentation stages for these editions were really crazy. We faced unpredictable circumstances, but we solved them. Step-by-step solving, a team of like-minded people, and motivation helped us a lot to organize the conference. The history of DSMIE conference series started in 2018 in Sumy. We found that the conference that unites researchers in the fields of design, simulation, manufacturing is urgently needed. Now it is the International Forum for Fundamental and Applied Research and Industrial Applications. It focuses on promoting and popularizing science, technology, engineering, and education. We are trying to do the best in our activities. Therefore, DSMIE conference series is the first engineering conference in Ukraine with an entirely English working language and changeable location annually. It is the first conference in Ukraine where selected papers were published as full-text papers by a leading worldwide publisher. It is a premier event in engineering that is recognized nationally and internationally. As I mentioned, the main idea of the conference implies the promotion and popularization of engineering science. Thereby, we are trying to expand the horizons and involve more and more people from different institutions. Sumy, Lutsk, Kharkiv, Lviv, Poznan is our way for 5 years, moving from east to west and otherwise. It doesn't matter the form of participation, traditional as in 2018 and 2019, virtual as in 2020, or hybrid as in 2021. We achieved our aim anyway. Each edition was unique and unbelievable. It is pleased that those who come to us in 2018 are still with us. Thank you very much for your trust. Thank you very much to your friendship. Each Ukrainian city has its uniqueness. Sumy is the spirituality of Ukraine. Lutsk is the fortress of Ukraine. Kharkiv is the mind of Ukraine. Lviv is the soul of Ukraine. It was always and will be for long. But the date of February 24 has changed everything in Ukraine. It forced change our minds and ordinary life. It forced rethinking about values. Chernihiv, Sumy, and Kharkiv were the first cities that met enemies. The inhuman intervention of Russia was a shock for ordinary people in Ukraine. February 24 is not only a tragic day for Ukrainian history, it is an alarm for whole Europe. Today is the 105th day of the heroic defense of Ukraine. Our beautiful cities were destroyed. Buildings and green parks transformed into ruins. The world supports us. We know about it and appreciate it. We are grateful to all countries, organizations, and people who helped us in this challenging time. The world stands with Ukraine. The world supports science, culture, music, and education. The world supports our colors. One by one, universities and organizations changed their colors to blue and yellow. We were amazed how Europe unites and helps us. Official statistics indicate that more than 8 million people relocated to safe places within Ukraine. More than 6 million people were forced to leave Ukraine. A lot of countries opened their borders. I must admit that one nation, among others, did a lot. Poland hosted more than 3 million people. Polish people opened their houses and shared their meals. It is impossible to evaluate their outstanding contribution. Why does Poland support Ukrainians so much? I know the answer. The Polish people know the pain of war. We are grateful to Poland and Polish people for all you do for us. Ми дякуємо Польщі та польському народу за все, що ви робите для нас. On behalf of Sumy State University, let me express my gratitude to Poznan University of Technology, Rector Professor Teofil Yasinovsky, and personally to all employees of Poznan University of Technology for their support of Sumy State University. In this difficult time for our motherland, we are grateful to the provision of humanitarian aid delivered to university clinics, Sumy defense units, and civilians in the most damaged regions. I am thankful to Olga Vakhrina from International Affairs Office of Poznan University of Technology for the initiative and coordination activities. The pictures handmade by Polish children were really amazing. I saw tears from the eyes of our brave defenders. Despite constant bombardments with heavy weapons and during the siege of Sumy, Sumy State University has not stopped educational and scientific activities for a single day. We believe in the future and we know that Ukraine is unified as never, and we will win. As you know, DSMIE-2022 was planned to be held in Sumy city. We were forced to relocate the conference to a safe place. We accepted the invitation of Poznan University of Technology to host conference with a great pleasure. The conference supported by our partners from Technical University of Košice, Kielce University of Technology, University of West Bohemia, Society for Robotics of Bosnia and Herzegovina, Association for Promoting Innovative Technologies, Springer Nature, and others. Also, we are grateful to all our industrial partners who supported us during the last 5 years. We appreciate the support of Alva Medical for their contribution to the conference. The principal value is people. Thank you very much to DSMIE team. Their involvement and hard work were crucial to the success of the conference. The core members of the team contributed to the success of this conference. Our vision is based on the 3 fundamental principles. The first one implies teamwork. The second one describes the primary mission of the conference, ideas exchange. The third principle certifies the quality of scientific results. The conference focuses on research challenges in the fields of manufacturing, materials, mechanical, and chemical engineering, addressing current and future trends in design approaches, simulation techniques, sustainability of manufacturing, and Industry 4.0 strategy implementation for engineering task solving. I am grateful to all keynote speakers who devoted their time to promoting DSMIE conference series. It was to admit that representatives from Poznan University of Technology have contributed too. Moreover, Professor Olaf Cishak was the first keynote speaker in the history of the conference. I am grateful to introduce the keynote speakers this year edition. Thank you very much for your acceptance and readiness to share the knowledge and experience. Remarkably, Professor George Christopher Wozniakas from National Technical University of Athens, Professor Dariusz Mazurkiewicz from Lublin University of Technology, Professor Szymon Wojciechowski from Poznan University of Technology, Professor Sahin Yildirim from RGS University, Dr. Vladimir Dolgih from Seco Tools Company, Mr. Christian Kogut and Mr. Przemysław Pasic from Intermarium. Our library is expanding. We have already published 8 books. Our previous books were indexed by Scopus and Web of Science Core Collection. I highly appreciate the partnership with Springer Nature and the contribution of all co-editors. Dr. Justina Trajanovska, Dr. Erwin Rauch, Professor Dragan Pirakovic, Professor Jose Machado, Professor Milan Edel, Professor Ivan Pavlenko, and Professor Alexander Lepochenko. I would like to thank members of the program committee and invited reviewers for their efforts and expertise in contributing to reviewing. Without it, it will be impossible to maintain the high standards of peer-reviewed papers. They devoted their time and energy to reviewing manuscripts. Our reviewers come from worldwide, represent 19 countries, and are affiliated with more than 80 institutions. Thank you very much. In my humble opinion, our achievements over the last 5 years are fantastic. The indicators of downloads and citations evidence the importance of the DSMIE conference series for the engineering domain. This year, we received 159 contributions from 20 countries around the world. After peer reviewing process, the program committee accepted 84 papers written by authors from 16 countries. Thank you very much to the authors for their contribution. These papers are published in the present books, achieving an acceptance rate in 53%. To sum up, 424 papers have been published in the last 5 years. We are strictly following the level of internationalization. A similar analysis was carried out regarding visibility issues. We are constantly monitoring the metrics to better understand current trends in research. These data are essential for us to plan the subsequent editions of the conference, particularly subtopics. Citations evidence the impact of the research results. The most cited papers are presented on this slide. Congratulations to the authors. International Association for Technological Development and Innovations agreed on the open access to full text papers. You can easily visit the conference via the link at our website. I would like to inform participants that extended versions of your research can be published in our partner journals. These journals are Management and Production Engineering Review, Journal of Engineering Sciences, Journal of Advances in Thermal Process and Energy Transformation, Assembly Techniques and Technology, and special issues of Machines and Sustainability. This year, the conference includes 6 keynote and 84 thematic presentations in 15 sessions. More than 350 participants will join us at conference rooms at Poznan University of Technology and Sumy State University, as well as virtual halls. I am thankful to session chairs for their acceptance and wish them and all participants fruitful working sessions. And please remember our motto: together we can do more for science, technology, engineering, and education. Let's enjoy the conference together. Thank you very much.
Thank you, Professor Vitaly Ivanov. Now I ask Oleksandr Gusak, Dean of the Faculty of Technical Systems and Engineering Efficient Technology from Sumy State University.
Шановні друзі, ми раді вітати всіх учасників, партнерів, спонсорів і організаторів ювілейної 5-ї міжнародної конференції конструювання, моделювання, виробництва, обмін інноваціями. На жаль, широкомасштабна війна Росії проти України в цьому році унеможливила проведення конференції в місті Суми, як ми планували заздалегідь. Але завдяки підтримці польських колег і за сприяння Міжнародної асоціації промислового розвитку та інновацій, конференція в цьому році проходить в місті Познань на базі Познанського технологічного університету. Мені приємно від імені організаційного комітету висловити глибоку подяку Познанському технологічному університету в особі декана факультету професору Олегу Чішику і співглаві конференції доктору Юстині Триновській за їхню ініціативу бути співорганізатором конференції DSMIE-2022. Я хочу подякувати нашим іноземним партнерам. Технічному університету міста Кошице, Словаччина, технологічному університету міста Кельц, Польща, Західночеському університету Чехія, а також Асоціації просування інноваційних технологій Хорватія, товариство роботехніки Боснія і Герцеговина, які своєю участю за роки її проведення підтвердили не тільки міжнародний статус, а і світове значення для розвитку галузей машинобудування, матеріалознавства, хімічної інженерії і механічної інженерії. Також хочу відзначити неоціненний вклад співорганізаторів конференції за попередні роки. Це Луцький національний технологічний університет, це Національний університет України, Харківський політехнічний інститут, це Національний університет України, Львівська політехніка. Наша спільна співпраця дозволила проводити конференції на високому науковому рівні. Я також впевнений, що і цьогорічна конференція буде тим майданчиком, на якому представники різних закладів вищої освіти представлять не тільки свої наукові здобутки, а і знайдуть контакти серед однодумців і представників промисловості для подальших якісних змін і кооперації зусиль майбутніх якісних змін та адаптації сучасної інженерії до світових викликів. Бажаю всім мирного неба, впевнений, що наступна конференція.
Thank you, Justyna. Ladies and gentlemen, welcome in Poznan, welcome at our university, our technical university. Welcome on 5th International Conference of Design, Simulation, Manufacturing with the subtitle, The Innovation Exchange DSMIE-2022. I'm very happy to see you healthy and ready for action. As a Dean of the Faculty of Mechanical Engineering, I have the honor to be one of the organizers of the DSMI conference. Of course, we know the plan was to meet in Sami. Thank you for accepting our invitation and come to Poznan. We all know what happened, what a tragedy it is, how unimaginable it is for all of us, especially for our friends from Ukraine. Please forgive me, but I will not refer to the political situation. And I'm very happy to see you so healthy and that we can meet in the DSMI conference here in Poznan. My dear friends, we join with you together with the Ukraine. Dear Dingusak, dear Vitali, dear my friends from Ukraine, of course, all of the organizational team, thank you very much for your warm words. Thank you for the trust for the organization of the DSMI conference. In the first, I would like to warmly welcome the Dean, my friend, Professor Alexander Gusak. Thank you for your words. Thank you for your commitment to defend the university. Thank you, Professor Vitaly Ivanov, General Chair of this conference. Thank you, Professor Ivan Pavlenko. Thank you for your trust and friendships. Thank you, Justyna Trojanowska, co-chair of the conference. Thank you, Professor Sławomir Lusiński, for your technical support, of course, and for your scientific. Thank you, Yulia. Hello. Thank you very much. And of course, all the organizational committee. Thank you, keynote speakers. Also, I welcome all of other guests and participants to the conference, including employers, of course, of our universities, PhD students, guests, industry, sponsors, representatives of our guests. Vitaly and of course Professor Gusak say our motto, conference motto. I would like say the same. Together we can. It's more important to do more for science, technology, engineering, and of course for education. I hope we are looking forward to meet on the next conference on 2023 on Sami. Welcome all of us in Poznan. Thank you very much. It's time for Dr. Justyna Trojanowska, if I could remember from our program, tak? Okay, the stage is yours, please.
Professor. At the end of opening ceremony, a few words from me. It is a very emotional moment for me, for maybe it will be better if I read my statement. First of all, I'm very happy to see you here today. And I thank Professor Vitaly Ivanov to the trust he has placed in us by entrusting us with hosting his conference at the Poznan University of Technology. But we should be in Sumy today. Yesterday, while exploring the city, you shouldn't meet near the old brewery in Poznan. you should meet in the fountain, near the fountain in Sumy. But it must be underlined that despite the hardships being experienced today by our Ukrainian colleagues and their loved ones, they have not stopped their significant contribution to the development of science. And this is really admirable. Maybe not everyone knows, but despite this difficult situation, scientists from Ukraine conduct classes and research, publish papers in the world's best journals, undertake internships, and organize conferences. Dear Ukrainian friends, you have shown the world that you are incredibly strong and brave. Your determination has brought you to today's success, and I'm sure that it will bring you further success because you are indestructible, and nothing will stop you in the fight for your and your children's freedom. And finally, happy birthday, because today we are celebrating the 5th anniversary of the conference. That's why we have here our balloons. It is also my personal anniversary because I met you 5 years ago. At the beginning of 2018, I hosted Professor Vitaly Ivanov and Professor Ivan Pavlenko at the Faculty of Mechanical Engineering. And later in June, I met in Sumy Dean Alexander Gusak, Professor Alexander Yaposhenko, and the rest of conference team and conference community. It was an amazing event that I still remember today. Thank you very much for those 5 years of intensive cooperation. I have to say that sometimes I cannot keep up with you, but thank you very much for allowing me to be the part of your team. The dates of the next editions of the conference are already on my calendar. I'm sure that we will celebrate the next anniversaries together. You are doing a great job. Once again, thank you very much for being here today, and remember our motto: together we can do more for science, technology, engineering, and education. Thank you very much. It's almost 9:30, so I think we can start the first keynote session, and I invite the chair, Professor Olaf Ciszak.
Thank you, Justyna. It's my great pleasure to provide a first keynote session. So, ladies and gentlemen, I am opening the first keynote session. We have 1 hour and 30 minutes. I think it will be good. The time is about 30 minutes for each lecture, with of course with question. And now, at the first our lecture, will be Professor Szymon Wojciechowski from Poznan University of Technology, and his first plenary lecture is titled "Selected Problems Related to Mechanics of Micromining Operations." Dear Professor, the stage is yours, please.
Thank you very much. Dear participants, thank you very much, Professor, for the introduction. Okay. Very much. Once again, thank you, Professor Ciszak. Dear participants, dear organizer, this is a great honor to me to be the keynote speaker during our conference, and it is a great honor to be the first one from the keynote speakers. Okay, let's start with our presentation. My presentation is entitled "Selected Problems of Micromilling Processes in Relation to the Mechanics and Dynamics of Process." During my presentation, I would like to focus on the state of the art related to the physical phenomena which occur during the micromilling processes, mainly the cutting forces, the minimum and cut chip thickness, the vibrations, and surface finish. Okay, the essence of ultra-precision microcutting. Microcutting is a process which is kinematically identical to conventional machining, but also it is fundamentally different in many respects, mainly due to so-called size effect. This kind of size effect refers to some phenomena occurring along the curved cutting edge of the cutting tool. Moreover, it also induces some phenomena which occurs in the workpiece materials. The range of microcutting can be defined considering following factors. The first of them is the uncut chip thickness, which should not exceed 200 microns. The second one is machine part dimensions, which are at least in a range from 1 micrometer to 1 millimeter. And in case of tool diameter, it can range from 25 microns to almost 1 millimeter. Moreover, we can divide, taking into consideration the accuracy of machining, into conventional, precision, and ultra-precision cutting. And conventional cutting is when the uncut chip thickness is at least 0.1 millimeter. Precision cutting is when the uncut chip thickness is contained within a range between 1 micron and 0.1 millimeter. And ultra-precision cutting is when the uncut chip thickness is not exceeding 1 micron. The fundamental question related to the micromachining processes is the definition of minimum uncut chip thickness. And this factor characterizes the state in which the decohesion process starts. So this is the transitional value at which the ploughing is not so intense and the chip is shearing. The general model, which describes the minimum uncut chip thickness, assumes that its value is proportional to the so-called normalized minimum uncut chip thickness, denoted by K, and cutting edge radius. So the majority of research, which is related to the determination of minimum uncut chip thickness, focuses on the estimation, on the assessment of the normalized minimum uncut chip thickness. Okay, some words in relation to the measurements of cutting edge radius. These kind of measurements can be made with some microscope, for example, Alicona or Keynes microscopes, but the problem is related to some variations of cutting edge radius value along the active length of cutting edge. So we have here some results of measurements related to the micro and mill with 1 millimeter, which was made of tungsten carbide, and we can see that average value of cutting edge radius for the new tool is equal to 2.7 micron with the standard deviation of almost 0.3 micron. However, the measurements were repeated for 100 times. The another problem is the variation of the cutting edge radius together with a cutting distance. As we know, the cutting distance is related mainly to the progressing tool wear during the cutting process. So the initial value of the cutting edge radius can be equal, for example, to 2 microns. However, during the micromilling process, at the cutting distance of about 600, 700 millimeters, we can see that cutting edge radius can reach up to 22, 23 microns. So this is a vast difference, which will affect consequently the minimum uncut chip thickness. And of course, the minimum uncut chip thickness will affect physical phenomena during process. For example, cutting forces or vibrations. Okay. So there are many researches which are related to the determination of minimum uncut chip thickness, and they can be divided into three fundamental methods. First one is the analytical method, which is based mainly on workpiece constitutive models, as well as we can also see the method which is based on identification of a stagnant point. In case of simulation methods, they are mainly based on finite elements models. Also, some of approaches are related to molecular dynamics, and the minority of methods are based on smoothed particle hydrodynamics. In case on experimental investigation of minimum uncut chip thickness, we can measure some physical phenomena during the cutting process. However, these are only the indirect methods, not the direct methods, and we can, for example, look at the machine surface, at the chips, we can assess the specific cutting force, and based on these quantities, we can assess the range in which the minimum uncut chip thickness occur. Okay, I can present here on figure 6 some area of research towards identification of minimum uncut chip thickness of various metals. These are some results from many different researches, and we can see here that independently on the workpiece material, we can see some tendencies. Namely, with a cutting speed, the value of normalized minimum uncut chip thickness is growing. This is related to the intensification of thermomechanical phenomena during the cutting process. As we know, the cutting speed increases the heat in the process and cutting temperature, so it plastifies the materials, and consequently, it inhibits the chip shearing phenomenon. That's why the normalized minimum uncut chip thickness is growing. And this dependency can be observed for different kinds of materials. The next section of this presentation is related to some approaches related to modeling of micromilling forces. I would like to present in figure 7 the distribution of forces on the cutting edge during the conventional cutting process in order to understand the essence and the difference between the conventional cutting and the micro cutting process. So we can see here the distribution of forces. These are the FT and FR forces, but they can be divided into forces which are located on the tool rake face, and they are called FTC and FRC. And we can see here also the so-called edge forces, which are located in the interface of workpiece and tool flank face. These edge forces are mainly related to the rubbing and friction phenomena. However, the FTC, FRC forces are mainly related to the shearing phenomena. Okay. In case of micromilling, we have to add one more constant, one more component. These are the ploughing forces called FTP and FRP. And as we can see, these forces are located onto the rounded cutting edge in the range in which the uncut chip thickness is lower than the minimum uncut chip thickness. Thus, these forces are characterizing the phenomena which are related to the pushing of some material in front of flank face, and they are related to the burnishing and ploughing phenomenon. Okay, now some equations, but don't worry, I will only some essence I will present. The analytical model of shearing forces assume that they are proportional to the so-called specific shear coefficients and area of cut per one tooth. In case of edge forces, they are proportional to the specific edge coefficients and active length of cutting edge. In case of ploughing forces, they are proportional to the ploughing volume and specific ploughing coefficients. So the main problem during the modeling procedure is to reliably estimate the values of specific coefficients and geometrical elements of cut. Okay, so I would like to present some kind of generalized model for a prediction of micromilling forces, and we can see here some input factors which are needed for the determination of these models. First of all, there are the geometrical errors of machining system. They can be neglected in relation to the conventional cutting processes because the value of these geometrical errors are not exceeding a dozen of microns. However, during the micromilling process, when the uncut chip thickness is in the range of microns, in a similar way, we have the geometrical errors, and they are mainly defined as the tool radial and axial runouts. Please come back. Okay. The next important factor is the tool geometry related to the cutting edge radius. Of course, the cutting conditions, which affect, for example, the values of edge and shearing forces. And we have to select the constitutive workpiece models, which are very important in relation to the characterize some thermomechanical aspects of the workpiece. Then we have to formulate the finite element model, and the outputs from this model are the chips, forces, and minimum uncut chip thickness. And these outputs can be put into equations of geometrical parameters of cut and equations of specific force coefficients. And ultimately, we can obtain the instant values of cutting forces in micromilling. Okay, some words about the geometrical parameters of cut. And we can see here the area of cut during the microball and milling process. And the section denoted by a black color is the nominal value of the area of cut. However, as I said before, the geometrical errors have significant meaning, so we have to include the factor of runout, delta E. And we can see this area denoted in the red color. This is the variation of the effective area of cut induced by the occurrence of the runout. The next very important factor in relation to the determination of ploughing forces is the ploughing volume and ploughing area. And this parameter is mainly related to the value of the cutting edge radius and uncut chip thickness. By solving these equations, we can obtain the values of ploughing volume, and then we have to determine also the ploughing constants. The next factor which should be included in models related to cutting forces during the micromilling processes is tool deflection and its effect on geometrical parameters of cut. As we know, the micro tools are very slender. The diameter of micro milling tools are, for example, 50 to 100 microns, and they have large overhead. So, on the other hand, slightly forces which act during the cutting process can cause the deflection of tool, which will affect the effective values of uncut chip thickness. The next factor which should be included in the modeling of micromilling forces is the effect of chip thickness accumulation. And this phenomenon results from the burnishing and workpiece elastic springback during micromachining. It induces the growth of instantaneous uncut chip thickness in the I tooth pass by the value that is not being removed in the I-1 tooth pass. So we can see here 3 tooth passes and areas denoted in red color and green color. And we can see here that when the instant uncut chip thickness is lower than the minimum uncut chip thickness, then the material is not being cut, but it is ploughed. So it is denoted by the red color. Then we can see the area which is denoted by the green color. In this area, the material is being cut. In the next pass is more complex situations, and we have some alternating switching from ploughing and cutting. Consequently, it affects the effective values of uncut chip thickness and, as we know, the cutting forces. Okay, in this figure shows the graphical interpretation of the chip thickness accumulation and deflections of the tool. And we can see here the effect of effective uncut chip thickness in function of time. In the preliminary state, in the transient state, we can see some accumulation of uncut chip thickness. It grows from pass to the tool pass, and it stabilizes when the value of effective uncut chip thickness reaches the value of minimum uncut chip thickness. Then we have some so-called steady state, but even in the steady state, we can observe some oscillations, and these oscillations of values of uncut chip thickness are related to the switching from ploughing, burnishing to the cutting action and reverse. So it will affect some variations, for example, vibrations and variations of cutting forces. Please, next slide. Okay, and figure 16 depicts the model chip formation time to total machining time in function of feet per tooth during micromilling of steel. And maybe this is not very good visible, but at the range to 2 microns, we have the burnishing dominant regime in the cutting process, because the majority of time in which the tool contacts with a workpiece, there is no cutting, there is a ploughing process. Only even when the feet per tooth is higher than 2 microns, the chip shearing dominates against the chip burnishing. So we have chip formation dominant regime. And figure 17 depicts the comparison of measured and predicted cutting forces in function of time per 3 feet passes. And we can see here, denoted by the red line, is the curve which represents the measured forces. The green and blue line are the forces predicted with the use of the proposed model with the chip thickness accumulations. And the last curve, the black one, is the traditional micromilling model, which is not including geometrical errors, deflection, and chip thickness accumulation. And we can see here that this kind of model, the traditional model, is not applicable to the ultra-precision micromilling because it underestimates the values of cutting forces. The similar comparison depicts figure 18, and we can see here the root mean square values of forces, which are modeled, experimented, and modeled with the conventional approach. And we can see here some oscillations, some non-linearities of forces in the range of feet per 2 from 0.5 micron to 2 microns. Some non-linearities are caused by chip thickness accumulation phenomenon. And as we can see here, the forces which are modeled with the use of this complex model are better in relation to the experimental ones in comparison to the traditional kinematic model of cutting forces. The next factor which should be included during the modeling procedure is the FEM model, which will include not only one tool pass, but two tool passes. Conventional models of finite element methods only assume that tool cut only once the material. However, it is not including some important factors, for example, the strain hardening effect and some other thermomechanical effects. And we can see here on figure 20 the comparison of forces, and the forces which are being calculated based on the model of FEM with the two consecutive passes are better fitted to the experimental ones than the ones which are predicted based on the model of only one tool pass. The next section is related to the vibrations in micromilling process. Even if the forces are very low during the micromilling process and very low uncut chip thickness occur, the vibrations in micromilling can be detrimental for the effect of the process. For example, they can cause the catastrophic failure of the tool. They can induce so-called chatter marks on the machine surface. So researching of vibrations during micromilling is very important and still very challenging. So we have here some sources of displacement in micromilling. The first group is geometrical errors of machining system, for example, tool axial and radial runout. The next one is dynamic mass imbalance, which is very important during micromilling because micromilling process is very often conducted with the rotational speeds about 600,000 to 100,000 revolutions per minute. So centrifugal force have significant meaning. The next aspect is, of course, tool wear, which mainly projects the geometry of the tool into the workpiece and affects also the values of forces and vibrations. And of course, the cutting forces, which cause the deflections of the tool during the process, and they are the main source of vibration. The next figures show the end mill displacement model during micromachining process. So we have here the nominal position of the tool and the position of the tool induced by runout, and also the position of the tool caused by the deflection. Deflection, of course, is caused by forces, and it is related to model parameters of the machining system. Okay, some equations. The general model of micromill instant displacement can be defined as the sum of instant displacements caused by the geometrical errors and the displacement caused by deflections related to cutting forces. So in order to obtain values of instant displacements caused by geometrical errors, we have to measure angle of tool runout, as well as we have to measure the value of tool runout. In case of differential motion equation of tool deflection, we have to solve this equation with the application of numerical methods. Moreover, we have to define the cutting force model because we have the right side of equation is instant force in relay direction. And of course, we have to define also the model parameters of the machining system, namely modal mass, damping coefficient, and dynamic stiffness coefficient. So in the next figure, I would like to present the generalized model of vibration during micromilling process. And of course, impact factors are as follows. They are the mechanical properties and construction of machining system, which affect the values of model parameters, the technological parameters of cut, macro and micro geometry of tool, of course, mainly the cutting edge radius, and cutting environment and kinematics. So when the next stage is definition of model parameters, and as well as the definition of cutting force model. And we can here use the mechanistic or hybrid cutting force model. Then we have to solve the differential motion equations. And ultimately, we have to solve the equations related to instant tool displacement. And moreover, if this model would like to introduce the chatter vibrations, we have to send once again the obtained instant tool displacements to the expressions of cutting force models in order to define the values of a cut chip thickness, which affect some oscillations related to vibrations. So we have the regenerative mechanism right here. Okay. And some results from the measurements and simulations. Left side and these red curves represent the model values of micro-milling displacement vibrations during the process, and right side are the displacements of micro-mill during the laser displacement sensor measurements. And we can see here some similarities in relation to the values and the shape of these curves. We can see also some local peaks which are related to the appearance of deflections per teeth. Moreover, we can see here some envelope of displacement which is caused by the geometrical errors of machining system. The next aspect is the generation of chatter vibrations, and these are the result of my own research, and they are related to determination of some constituents of frequency of vibrations, which are related mainly to the appearance of chatter frequency. And we can see here that in case of micro-milling with very low values of feet per tooth, for example, 1 micron and 2 microns, we can see here some constituents with a frequency of about 1 kilohertz, which are related mainly to the chatter frequency. This is in contrast to the traditional milling processes, in which when we define the stability lobe diagram, in this diagram we have some range of actual depths of cut, and at the low values of depths of cut, the process is always stable. However, in case of micro-milling, in case of very low feet per tooth and actual depths of cut, the process is not stable. It has some instability. Probably it is related to ploughing mechanisms and chip thickness accumulation phenomenon. However, this requires which affect the machine surface. As we know, in conventional machining, the machine surface is mainly affected by feet per tooth, by tool diameter, and corner radius. Moreover, the cutting speed. However, during the micro-milling processes, very important are workpiece mechanical properties, its structure, grain sizes, crystallographic orientation and anomalies. Moreover, of course, the cutting parameters, tool macro and micro geometry, and mainly the cutting edge radius, as well as the helix angle. Moreover, the geometrical errors of machining system, dynamical properties of machining system, which affect the vibrations, and micro-milling kinematics. So in order to create the generalized model of surface finish during the micro-milling process, we have to create two different sub-models. The first one is the FEM model of chip formation, which should define the minimum uncut chip thickness and specific force coefficients. Moreover, if it is possible, it is good to formulate the three-dimensional model, which can assess the elastic spring back of the material, side plastic flow, and material anomalies. The next stage is the definition of micro-milling dynamics model, which is needed for the definition of instantaneous tool displacement. And these two models, the outputs of these models, are put to the generalized surface topography model. Okay, thank you. Okay, this figure shows this is a very simple model in relation to the previous one. However, it includes both the effect of kinematic geometrical projection of cutter into the workpiece. Moreover, it also includes the effect of so-called cutter displacements enveloped, which is affected by the deflections as well as the geometrical errors of machining system. Okay. And we can see here some result of this modeling. We have the feet per tooth, which affects the surface roughness height and average surface roughness. And we can see here that the traditional model, which is denoted by the blue color, traditional kinematic geometric, is totally inapplicable to the definition of surface roughness, because it is not including vibrations during the process. We can see here also the results from measurements denoted by the red curve, and the green line is related to the ones which are calculated with the application of the proposed model. We can see here very good conformity of the values of surface roughness, which were modeled on the basis of the model which includes the cutter displacement envelope. Moreover, we can see here also the yellow curve, which affects only the geometrical errors of machining system. So we can include only the actual and real runout. We can see that these values are overestimated because the deflections causes smaller values of cutter displacement envelope. Last aspect of the presentation is related to the effects of milling of curvilinear surfaces with micro ball and mills. And we can see here a very important factor in micro and milling. This is called effective diameter of the tool. And we can see here that in relation to the direction of cutting process of upward and downward ramping, we can see that there are different values of effective diameter of the tool. The effective diameter of the tool significantly affects the cutting speed values. So in case of upward ramping, the cutting speed is always higher than 0. But in downward ramping, the DEF4 is located in the vicinity of tool tip. Thus, the cutting speed in this area is very low, so it induces very large plastic deformations of the workpiece, and this will affect the surface roughness. So we can see here the comparison of the measurements of surface roughness, and the blue chart denotes the values of surface roughness which are obtained on the basis of upward ramping process, in which the cutting speed is higher than 0. And in case of downward ramping, we can see that the values of surface roughness are significantly higher. We can see also the surface topographies. The surface topographies after upward ramping are very smooth, but in case of downward ramping, they have many asperities, irregularities, which appearance can be related to the ploughing phenomena related to the low cutting speed during the process. Okay, and this chart shows the atomic force microscopy images made during the ultra precision micromilling process with very low values of feet per tooth. And the first figure shows the process in which the feet per tooth is lower than the minimum uncut chip thickness. So the irregularities which are formed during the process are related only to the plastic deformation and to the ploughing domination phenomenon. In case when the feet per tooth is higher and equal almost to the minimum uncut chip thickness, we can observe also some discontinuities formed by microcutting. The similar situation in case when feet per tooth is equal to 2 microns. However, in case when the feet per tooth is higher and equal to 2 to 7 microns, we can see also some grain chunking, which is induced by the cutting edge, and also the projection of edge microgeometry. So during the micromilling process, if the feet per tooth is too high, the projection of cutting edge is very large. So we have some micro irregularities which are not formed by the process itself, but by the projection of tool geometry into the workpiece. Okay? And based on the carried out research and state of the art, we can formulate the following conclusions. First of all, the cutting force models, which should be applied during the micromilling processes, should include many important factors, as for example, minimum cut chip thickness accumulation, and deflection of the tool. In case of finite element modeling, the models should include the consecutive tool passes, and maybe they should be formulated in 3 dimensions in order, for example, to estimate elastic spring back of the tool or plastic deformations. The accurate dynamics model for micromilling should take into consideration the role of damping and ploughing forces, chip thickness accumulation, and geometrical errors of machining system. And the role of tool microgeometry changes on the formation of surface texture and cutting forces should be further studied. Thank you very much.
Professor, perfect time. Please stay here.
Okay.
My dear, a question to the professor for his speech. Professor Bawalski, please.
Okay. Okay. The effect on the temperature and what was the value of temperature during the micromining process. This presentation was some called of state of the art. So it has many researchers from many studies, and temperatures were very different in relation to the workpiece materials. But I think from the measurements that temperature in case of cutting of steel will be about 500 Celsius degrees to 700 Celsius degrees, for example. But it is dependent on cutting speed, and it is dependent on other cutting parameters.
Please come here.
Just closer to the microphone, please. Closer to the.
Dynamics process with load and what you think about our natural frequency in your process?
And natural frequencies. Okay, so this is very important aspect in relation to the dynamics of the process, because the natural frequency.
You need to maximum speed or not speed, frequency, natural and load, and we have resonance.
Yeah. The resonance phenomenon. This is the large problem during the micromining process, because the preliminary studies should include the impulse test in order to define the resonant test, the resonant frequencies of the machining system. For example, the resonant frequency of the tool, of the spindle, and of the collet. So when we are selecting the rotational speed during the process, we have to be between these resonant frequencies. But even if we do this, we can see some natural frequencies which can be related to chatter. Yeah, this is very difficult because there are very high rotational speed. So this is very high probability to be near the resonant frequencies. Thank you very much for this question.
Thank you, Professor. Have you any question from the internet, for example, from Summit University?
No, but I have one question.
Okay, please,
I
Justin.
the paper, you can read it.
Okay, thank you very much. What is the effect of minimum uncut chip thickness on surface roughness? Okay, thank you very much for this question. The effect is very large of the minimum uncut chip thickness, mainly in the range of very low values of feet per tubes, because at this range, the material is not effectively cut, but it is being ploughed. So in the effect, we have very high surface asperities, which are not related to the kinematic geometric projection, but to the plastic fash of the workpiece. So the large problem is that during cutting with very low feet per tubes, we don't have, for example, grain chunking, but the other problem is plastic deformation of the workpiece. So this is inevitable during the process. We can only use the tools with very low cutting edge radius. For example, the diamond tools are cubic boron nitride tools. However, the diamond tools cannot be applied in relation to the steels.
Okay. Thank you, dear professor, for your very interesting speech, for your answer to our questions. Justin, that's one of the piece for our professor. Okay, thank you. Once more, thank you.
Thank you very much. Thank you very much, Professor. This is an honor for me. Thank you once again to participants. Thank you.
Dear, the next keynote speaker will be Professor Dariusz Mazurkiewicz. He's a professor of mechanical engineering at the Lublin University of Technology. His research interests include production engineering, especially regarding maintenance and technical infrastructure reliability. Dear professor, will connect with us by internet. Yes, Dariusz?
Yes, I'm present.
Okay, great. Thank you, professor.
Shall I start?
Moment. because our technical team should prepare your presentation in the internet platform.
We can see the presentation now. Okay, so I think the presentation is available, so I can start my speech. First of all, thank you very much, dear organizers, for your invitation for me to join the conference as a keynote speaker. It's a great pleasure for me to present this speech. Thank you very much also for your great job and very good organization of the conference. I'm very sorry that we cannot meet in personal. However, I hope next year the situation, all the circumstances will be completely different, and we'll have a chance for regular conference, not a mobile one as this is right now. So my presentation is titled Digital Twin-Driven Reliability Research Challenges, and this is related to some challenges we have right now concerning the needs of the modern industry, especially concerned with the industry 4.0 philosophy, with information and communication technologies, which are more and more popular in production companies, and also some challenges related also to new possibilities we have in modeling, in simulation of real world as digital twin is, for example. This is why for this purpose I will try to present you what are the needs, what kind of solutions we can find with the use of digital twin, why is it considered as a key research possibility right now, why so many researchers are involved in researches with the use of digital twin, and also what kind of research gap we have to fill in the nearest future. Innovation and reliability are two topics who are very close related to each other, especially if we will take into consideration the modern industry. By the way, all these three features which you can see on my slide at this moment come from Poznan region companies, production companies. Automotive industry presented on these features is a kind of high innovation industry where usually all the most modern technologies solutions are applied very, very early. Usually, automotive industry is also considered as the first sector where industry 4.0 is implemented. High speed of production processes, extremely innovative productions machines, robots, information and communication technologies make a lot of problems for these companies, especially in the field of reliability. Extremely or very highly developed production machines require also very high reliability of their elements or themselves in the whole, which is required by the industry, working usually 24 hours a day, 7 days a week. This is why the production equipment must be kept in a very high efficiency, able also to work during 24 hours, 7 days a week. And this can be ensured by effective control of technical conditions of machines and devices, which are usually very innovative in the production plant. If we will take into consideration the requirements of industry for zero, where automation and cloud innovations play an important role. This makes the production system this makes a lot of new challenges for the production system and its full operational efficiency, which will be as effective as possible. This makes necessary a lot of different reliability or maintenance solutions which should be applied to achieve high reliability of all the machines used in the production plant to allow the production process, the manufacturing process to work in constant conditions without any failure or stops during the production process. On the other hand, we have a lot of new solutions which are available right now. For example, first of all, everything becomes smart. The word smart is used for many different applications. We have smart technologies, we have smart assembly, smart reliability, smart and intelligent sensors, and so on and so on. Everything becomes smart right now. Also, as a result, factories or production plants are transferred into smart factories where machines, smart sensors, and robotic platforms on the shop floor are used on everyday application, producing a lot of data registered by all these intelligent sensors, machines, and other elements of the production plant. A high integration of context data coming from so many different machines, so from so many different sources, is necessary to improve efficiency and to speed up the production process. This is why nowadays we very often talk about a big data problem. We receive a lot of data from different sources, from different machines and different sensors. So big data analytics is considered as a kind of huge research challenge in the 21st century. Also in the field of reliability, where a lot of data concerning failures, maintenance actions are available from the monitoring and other production processes available for evaluation, of course. This is why we can right now distinguish two important research and development challenges in the field of reliability and data processing. In the case of reliability, a key challenge is predictive maintenance, which allows not only just very simple action to failures which may occur during the production process, but which makes possible the prediction of potential failures in the future and creation actions which will allow us to avoid them, making the production process as efficient as possible. This makes also important maintenance management, also expert systems, as the information and communication technologies become more and more popular, and also computerized maintenance management systems, CMMS. In the case of data processing, there are several different data processing technologies which are developed, especially right now. For example, classification, identification, also processing complexity reduction, as the problem of big data is very important, and as well expert systems, the same as in the case of reliability, because we want machines, data systems to be as intelligent and as possible, able to make decisions by themselves in real time. In predictive maintenance problems, for example, many issues are still open from a modeling point of view, especially like dealing with high dimensionality data fragmentation, the need of adaptive solutions, and for interpretable models as well. If we talk about problems connected with failure predictions, there are a lot of aspects in analysis, in modeling, we do not take into consideration right now. Of course, we are very good in technical aspects, monitoring measurement systems are highly innovative, but on the other hand, we do not take into consideration, for example, non-technical aspects or qualitative features. For example, system should replace man at selecting a prediction method and taking decision about the time of repair works. This is why the aim of human error action or human error influence reduction with the use of expert system is very important. Also, prediction and decision model should dynamically react to changing production conditions, as everything changes all the time. In addition, sustainability requirements are also necessary sustainability development. It means economic issues, seasonal issues, human influence, social aspects, and so on, and so on. For this purpose, together with my colleagues from Rzeszów University of Technology, we lead for a few years specified research. They are also related to production process and especially machining process. The first step which we have implemented in our researches was the cutting tool condition assessment model which we have created for real-time supervision system. On the figure on the left side of the slide, you can see a typical production machine tool, which in Rzeszów University of Technology is implemented with several sensors, acceleration sensors, axis force sensors, spindle velocity sensor, and so on and so on. This way, we are able to collect huge amount of data concerning the production process, which adequate analysis allows us not only to make some predictions and modeling from the reliability perspective, but also which can be used for production process optimization. One of the results we have achieved is the support vector machine implementation in cutting tool condition assessment model, as you can see on this figure. The upper part of the figure shows the historical data which we collect with the use of measurement system and all these sensors which were presented on the previous figure. And with the use of support vector machine and nonlinear mapping, we can separate features, achieving this way mapped vectors, and with the use of weights we achieve a kind of classifier. This classifier, when implemented to current data and input current data which we collect real time right now, having real-time information about the machining process, when we will implement this classifier and in addition ARIMA identification, we can achieve two different solutions. First of all, we can say what is the tool status right now. We can make, in other words, tool classification, saying is the tool correct or is it in failure. And on the other hand, we can also predict the remaining useful life, saying, for example, that this tool in its current state can work during the next, for example, 50 hours without changed production process parameters. This is not everything, of course. Together with Rzeszów, we continue our researches, especially taking into consideration a digital twin, which is a kind of extremely interesting tool or solution for modeling of production processes, for modeling and in reliability, especially as a kind of industry for zero applications, and also if industry for zero gaps. As a very hot topic, digital twin approaches have been designed and implemented to date, which examples, a lot of different examples we can find in references. However, when we will analyze deeply these applications, we will notice that most of them lack a comprehensive review of digital twin benefits by considering both engineering, production, life management, and business innovation as a whole. This means a kind of research gap we have to fill up. Of course, digital twin have a lot of different industrial applications. I will present them very shortly on this slide. Of course, we can use digital twin model on design phase, for example, as a virtual evaluation and verification of the real world model. We can use it on the manufacturing phase. This is something what we do, especially for real-time monitoring, for production control, and for reliability, which is also concerned with the service phase, where predictive maintenance in reliability plays an important role. Of course, in retire phase, digital twin applications are also possible. Digital twin, in a short presentation, is described as one of the strategic directions for manufacturing enterprises to progress. It is designed mostly to improve manufacturing efficiency, and is designed as a digital duplications of real-world object which can be analyzed together with the real-world object in parallel due to possibilities which we have in industry for zero, thanks to, for example, cyber physical spaces. Of course, as in typical production, data acquisition is extremely important, and also data transmission and data analysis. The data which we have available without proper analysis is usually useless. Of course, there are a lot of technological architectures for digital twin related to data technologies, high fidelity modeling or model-based simulations, and due to its potential to generate accurate data from physical space and virtual space at the same time, and with the possibility to analyze and make a kind of modeling of real-time data also in real time, digital twins represent the future technology for lifetime assessment especially. This is also one of the challenges for us with our colleagues with Rzeszów. This is something what we do right now. As you see, the support vector machine solutions, which I have presented a few slides before, can be used in digital twin of CNC machine tool for its cyberspace on the right side. Of course, the machine which we have in the lab in Rzeszów is a source of real-time data, while the data twin analyzed or modeled for different applications in the same time makes possible smart executive actions for different purposes, including also predictive maintenance with fault diagnosis, fault forecast, remaining useful life prediction, and smart maintenance. Of course, we have to making researches on this kind of digital twin applications in production engineering. We have to answer a lot of questions which are summarized on this slide. For example, how can time series data collecting during the operation be used with the support of digital twin to improve the availability and sustainability of production assets, and also how can smart maintenance be scheduled and adjusted instantly to optimize the life cycle availability and sustainability of production process. This makes necessary further research for predictive maintenance framework based on machine tool and its digital twin, as presented of this feature with the implementation of intelligent manufacturing, industrial Internet of Things, machine-to-machine communication on all these solutions which are typical for industry 4.0, we can improve the machining process itself, and also we can have an influence on the reliability of the machine tool, or separate key elements of this machine. With the help of the digital twin and big data technologies, a virtual simulation model of the real machine tool can be established, and the entity status could be fed back in real time with the use, of course, of data collection, data processing, data pre-processing first of all, and post processing for data-driven digital twin applications in machining. For example, machine learning and digital twin-based algorithm for smart technological infrastructure in sustainable environment can be used as presented on this feature. As we have seen before, we have the same physical machine tool equipped with all the sensors. These sensors allow us to get to collect data concerning current and previous faults, and also collect the data concerning the running status of the machine. With the use of mathematical modeling, machine learning, decision-making tool, and so on, we can achieve results in control mechanism of the process, creating smart interpreter or smart executive mechanism, which is able to make automatic executive actions to allow the production process to be as effective as possible. On the other hand, we can have also intelligent model evaluating our results, which we can use for smart maintenance or smart reliability. It's the same maintenance and the same reliability as we had before. However, with the use of expert systems and some kind of intelligence makes the maintenance smart. This way, the virtual simulation, previous one, please. This way, the virtual simulation model judges whether the physical model will generate a fault based on the real-time state data and can effectively reduce the failure rate. As you can see, data creation and development requires extensive knowledge and applications on different technologies to ensure seamless integration between the different components. To overcome this challenge, we have to identify adequate communication, representation, computation, microservices, and other essential research challenges, forming a technology stack to ensure a coherent and consistent digital twin implementation, and this is the gap we have to fill. The next slide, please. As for the final conclusions, we can say that manufacturing companies operating in today's competitive business environment are forced to constantly meet the needs of their customers, offering them the highest quality products while ensuring the best sustainable results. In order to achieve this, the decision makers who have an impact on the functioning of the enterprises need to make efforts to continuously monitor and improve a production process, while the difficulty of the production management process constantly increases, making new requirements, especially for the reliability and the reliability engineers. There is no doubt that effective and intelligent manufacturing data source integration, connection, and adequate implementation and data processing with automatically performed executive actions are highly required by innovative factory, especially in the case of Industry 4.0 and information and communication technology requirements. Many experts point out that future research directions in engineering will focus on the creation of intelligent sensors, we know this very well, and their integration by means of digital systems and intelligent platforms, in which digital twin plays also an important role, what led to a growing interest in the concept of the digital twins, its capabilities and potential applications in productions engineering. Also, in the case of examples and researches performed by us, as I have presented during my presentation. I think it's the high time to finish. So thank you very much for your attention, and thank you very much one more time for the possibility to make this presentation during the conference.
Okay. Thank you, Professor, for your very interesting speech. Everyone knows what the digital world is present between us. And we have the time, though, for the one quick question. Please. Maybe from the internet? No? Any questions? Everything? I think everything was very clear. Once more, thank you, Professor.
Thank you very much.
Thank you very much.
Pleasure.
It's my pleasure too. The next panelist will be Christian Kogut and Przemysław Pasich. They represent the manufacturer, the company, sorry, Intermarium. Mr. Christian Kogut is the member of the board and international sales director in this company, and Przemysław Pasich is the simulation engineer in this company. They will present the lecture in subject process simulation technology in modern didactics on the example of decision games created in Flexim software environment. My dears, okay, the screen, the internet is yours. Please, the stage. You can start. Are you ready?
Yes, we are ready. Hello, everyone. Good morning. I will let myself to present our screen and our presentation. First of all, thank you very much for invitation. My name is Christian Kogut. I'm International Sales Director at Flexim Intermarium. And thanks to the generous invitation from the organizers of this conference, together with my colleague Przemysław Pasich, we would like to introduce ourselves as a company and the tools that we provide for modern education. I was happy actually that previous speaker, Professor Mazurkiewicz, mentioned a digital twin because in his presentation, because digital twin is something what you can create also using our tool. Anyway, our presentation will be a bit different than the previous ones, and of course, please take under consideration the fact that we are not the scientists as the most of esteemed participants. Our presentation will include the introduction of our company, very short, and our offer for education, and also the reasons why to use Flexim and cooperate with us. Then introduction of our new product, simulation decision making games. And after all, I hope it will be some time for a quick question and answer session. Flexim Software Products Incorporation. This is the American company based in Utah, and this is our main business partner and provider of main product that we sell and use. And they have a worldwide distribution network, and our company, Intermarium, is probably one of the largest of their distributors. We are independent Polish company with headquarters in Kraków. We use Flexim in our project since 2012, and since then we are a partner of Flexim in Poland. While from the end of 2016, we became an exclusive Flexim distributor in Central and Eastern Europe. Currently, we are responsible for 25 countries, which you can see highlighted with yellow color on the map. And also we develop a network of our own local representatives and sales agents. We offer the user licenses, first of all, so for commercial use and also only for didactics. We offer training of various types and services like the simulation games that we would like to present today. Now, what are the reasons to implement and use Flexim at your laboratories, departments, and to cooperate with us if you are not doing that yet? First of all, with Flexim, you gain yet another platform of possible cooperation, also international, with other universities. It means more scientific articles, more international projects, more internships, and more grants. Currently, Flexim is used in hundreds of universities worldwide, and at least at 60 universities in our region. Although Flexim is widely used in education, I have to underline that Flexim is a tool created to be used primarily in business, in industry. Therefore, you can create, with using Flexim, one more platform for a real cooperation with business, with your business environment. It can be used for student projects, degree theses, and as a tool for projects under the EU grants or the national grants. It gives you a chance to become a kind of a simulation competence center for your local business environment. We have samples of successful and interesting cooperation of that kind. Currently, we as a company cooperate with nearly 100 businesses from various industry areas. Obviously, the group of reasons why Flexim is a simulation tool you would like to use, the another group, are coming from its technical advantages. Here you can see some capabilities of FlexSim that we consider as advantage against the most of the competitive tools. But I would like to mention three more general things. FlexSim is a leading simulation tool on its class, and it is a general purpose software. So it might be used in various departments, faculties, and in various research areas. The other thing is that it's designed for modeling, visualization, control, and optimization of logistics and manufacturing processes, mostly, but not only. And this is very practical tool. So basically, it's intuitive and really, really user-friendly. FlexSim is also enriched with useful features. So the experimenter lets us to create multiple scenarios of simulation and automatically analyze all of them at the same time. OptQuest is a more advanced add-on, which allows us to change the approach from what if to what's the best by automated parametrical optimization. And ExpertFit helps us to find statistical distribution that is most relevant to the empirical data that we want to use in our simulation. Also, FlexSim provides database connectivity. If you would be interested, you can easily try FlexSim for free by downloading the experts version from flexsim.com. And following that, most probably I or one of my colleagues will try to get in touch with you. But I hope that after our presentation or after trying FlexSim Express, you will get in touch with us first. That's it from me for now. So thank you. And my colleague, Mr. Pasich, will present the simulation games to you. Thank you.
Thank you, Christian. I am going to first ask, is my screen visible? Can you see my screen?
Yes.
Okay, brilliant. So I'm going to present to you some of the simulation games that we made for and in cooperation with Wrocław University of Economics and Business. The scenarios were provided to us by the very lecturers of these universities, so we made these games to the specifications that they requested. In the first game that I am currently showing on my screen, we are going to take on a role of a designer of a production line. It is going to be up to us to decide what the layout of this production facility is going to be. But first, let's take a look at what the production flow is like here. So we will start off from the raw material storage, where we pick up some raw material, transport it to the production line that in this case consists of 3 stages, during which the raw material gets transformed into the finished product, ready to be picked up by a forklift and placed in the finished goods storage. Our task is going to be to fill this room with as many red boxes as possible within 1 hour. So if we speed up the simulation, we will see the material buildup. And we will see that we managed to produce nearly 2 stacks of red boxes in the current state of this factory. So let's have a think about what we can use this game to, what kind of lessons we can teach our students using this game. Even in a layout simple as this one, we will always have a bottleneck. So taking advantage of the fact that FlexSim shows us in 3D the current state at which the factory is, we can, for example, train the students to gain the intuition of guessing which machine is the bottleneck just by looking at the shop floor. In this case, we can see that the machine in front of which the biggest queue starts forming is probably going to be our bottleneck. If we are people who are more driven by data, we might want to decide to teach our students how to analyze, read, and make sense out of utilization graphs. FlexSim allows us to collect that kind of statistics in real time. Each of the graphs here corresponds to one of our machines, and indeed, it seems that the middle machine is being utilized the most. At this point, we might want to ask the question of, what if we had two machines of the second stage? Testing this hypothesis is as easy as just resetting the simulation, dragging and dropping an appropriate machine into the 3D environment, and then adjusting the layout to accommodate the change that we've just made. So let's just place it right next to this one. And when we run the simulation again, we will get the instant feedback of the effects of the change that we made. Firstly, we see that both of these machines work. They process the material. And in order to gauge whether our decision was good or not, we can take a look at the throughput of our factory. So how many boxes do we manage to produce after 1 hour? And we see that it is indeed more than 2 stacks. So we get nearly instant confirmation that our hypothesis that the middle stage was a bottleneck was indeed correct. This is how a sample lesson could look like. So we start off by presenting to the students some new concept or a new challenge, in case it was the concept of a bottleneck. Then we get the opportunity to teach them some tools to analyze and try to solve the problem. So in our case, it was the utilization graphs. And then we can give the students the chance to test their understanding and to explore some hypotheses by just giving them this interactive simulation to, let's say, play around with. So what else is it that we can try and teach the students? Let's complicate things a little bit. So far, we've just been making red boxes. So I'll change the settings to introduce a new product type. And let's see how it goes. So again, if we run the simulation, this time we can see that the new product type of green boxes appeared. The production process for these two product types is going to be just the same. That is to say, it will take the exact same amount of time for the red box to get through this line as it is going to be for the green one. So our first intuition might tell us that it won't really make a difference, right? If we run the simulation, again, we should see that we made more than 2 stacks of boxes like we did before. But the simulation has just ended and we are short of 2 stacks. Again, this is one way in which we can visually represent a concept in production flow. In this case, it is the effect of setup times on the overall throughput of the factory. This is the point at which we could, again, stop the demonstration and open the floor for the students to start formulating some ideas, maybe hypotheses, try to brainstorm how to mitigate this issue. One way of doing that could be, for example, to set up a parallel line. So again, we drag and drop machines into the 3D environment to match the other one. To speed things up, I'm going to just introduce everything into the environment. So we have just the same line here at the top and at the bottom, but we will decide to dedicate the top machine to just making red boxes and the bottom one to just making green ones. So when we run the simulation, we will see that indeed these flows have been decoupled. They have been made independent. So when we run the simulation, we should expect that since we eliminated the setup time from our flow, we should be able to be producing roughly more than 2 stacks of each product. Since we have 2 parallel lines, we can start comparing them. We can ask the question, what if we actually had the machines arranged into a U-turn? Or what if we decided to clump all the similar machines together into work cells and arrange the factory in this way? Or what if we arrange them in a hexagonal grid? Or what if? Flexim gives us the freedom to just explore some layouts and experiment. The game has been set up in a way that it started off pretty easy, just a single line, one product, and then it's up to us, the teachers, to introduce new concepts and decide on when we introduce them, the pacing of the lessons. In this game, for example, we have the difficulty levels which reflect various settings that govern this simulation game. We can decide to introduce the concept of machines breaking down to maybe, for example, explain the statistics, that the statistical distributions that govern the mean time to repair and mean time between failures. We might want to decide to make it more challenging and set up a scenario that if machines are far enough apart, we won't use the operators to move the work in progress between stations, but rather introduce a new mode of transportation, which will be a forklift. So this way we can teach the topics of internal logistics within a factory. We can decide to limit the number of operators and then have the students try to figure out what the optimal assignment of operators to tasks would be. Or we could, for example, take advantage of the fact that each of the machines here come in variants that will differ in price. Some of them will be more expensive, but will have shorter setup times and higher throughputs. Or maybe we can stick to cheaper machines that will not get the job done as quickly as the more expensive ones. That way you can teach the students either the concepts of optimization or working under a limited budget, since each of the machine costs us money. This game strictly has to do with the topic of industrial production, but it doesn't necessarily have to be this theme. We have made games that, for example, one game in which you take on the role of a farmer, you get to decide what crops you grow, how you respond to various weather conditions, to diseases. Another game in which you take on a role of a human resources representative. You will simulate the process of going through an interview, screening for candidates for a job. Some of these games take place in this environment, and some of them are actually played using the virtual reality, the VR headsets. So you put it on and play the game by well, being in there. And a game that I want, another flavor of a game that I wanted to show you is this one. This one is a logistics game. We are taking a role of a manager of a company that delivers packages. So what we are currently looking at is the central part of Wrocław. This game features the 3D model of the city. It's the scaled version. So hopefully some of you recognize the panorama of Wrocław. And so our task is going to be to satisfy orders. At the beginning of the simulation, we get a generation of orders. It will just take us a second. Each order will just represent a person waiting for a package to be delivered to them. So if we zoom in, each of these little flags represents a person and an order to satisfy. The decisions that we get to make has to do with these transportation hubs. These are our assets that we can decide to place in the map wherever we desire. Each of them will have a range of orders that it will serve. For each of them, we can also define its capacity. So how many vehicles like bicycles, electric cars, or combustion engine cars are going to be servicing this station? We can also decide to change the range that it services. And then playing around with this decision space, let's say, we can introduce topics that are going to be relevant in the concept of logistics. When we run the simulation, we decided that this is the setup that we want to run. We will see that the game is even simulating the process of collecting the packages from the hub and then dispatching all these vehicles that we decided, was it bicycles or electrical cars, to drive around the neighborhood and to deliver the packages. To make things a little bit more interesting, we decided to ban cars from the central part. So bicycles, for example, can travel in the middle bit, while combustion engine cars have a ban, are not allowed inside the central part of the city. And once we run the simulation, we will see how many orders we managed to satisfy. Each of the flags that disappeared was effectively a satisfied order, and all the flags that remained after the simulation are the orders that we didn't manage to serve. Unfortunately, this is about enough time that I have to show you the games. So if you're interested in finding out a little bit more about the other games that I mentioned, or yet other games that I didn't even mention, I encourage you to get in touch with us. Our contact details, I believe, will be in the conference materials. Thank you for listening.
Thank you, my colleagues. How can you see the digital world is around us? We have a time for quick questions from the internet. Any question? Nothing. Everything is clear. And from our room? No. Some aspects is really a no for us. Thank you once more for the very interesting and inspirational your lecture. We will see on the next session panels. I see in the program, in the conference program. Thank you once more.
Thank you. It was a pleasure.
Bye. My pleasure. Ladies and gentlemen, I close the first keynote session. I think it's a very good time to the coffee break, to our opposite, to the next room, please. We should go. Thank you. Sami start.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Hello to everyone. У меня выключен микрофон. Okay, dear participants, let us start the session number 2. This keynote session is focused on research in engineering technologies and artificial intelligence. And I am happy to introduce the keynote speaker from Turkey, Erciyes University, Professor Sahin Yildirim. He has a huge experience and a well-known scientist in
open dynamics engine. There is also vibration analysis of experimental double bridge crane system by using neural networks, analyze and control of welding trajectory in industrial robots, and finally design an experimental application of material classification prototype system. Let's see first topic of my presentation. It is a kind of system which is designed for blind people. It is a kind of mobile robot. In this practical application, it is aimed to design and produce prototype system. The system consists of mobile robot and vision systems and a kind of software we can use LabVIEW. The main target of this application, a kind of mobile robot, enables blind person to get from some place to other place, determine path without any errors. You can see our flow process theorem for this kind of experimental applications. Initially, we should find path planning. And then path planning consists of a kind of controller design and localization and building map. This system shows, can you pass other slide, please? Yes, I showed this flow process theorem. And then next slide, please. Yes, this is our experimental setup for mobile robot and platform. You can see on the right side, this is top view of the setup. It consists of mobile robot. It is marked for localization and it is a kind of software LabVIEW and artificial neural networks. There are some obstacles. Without touching and contacting any obstacles, the mobile robot should follow exact trajectory without errors. You can also see path planning. This is a kind of algorithm. It is presented to improve capabilities of A-star algorithm, which is the best algorithm for path planning. Next slide, please. Yes, you can see software. This software consists of A-star algorithm, the algorithm used for exact trajectory, following without touching any obstacles. We can also see general polynomial and B-spline trajectory for this kind of robot. As I mentioned before, this software is a kind of based on LabVIEW environment. You can see on the left side, the robot is following exact trajectory without small errors, without touching any obstacles. Next, please. This is our controller design. This equation shows kinematic equations with linear and angular velocity of our mobile robot. We can also see on the right side a kind of vector representation. On the right side, it's a kind of 3D view, a kind of simulation software. You can see on the right side, there is some small errors, but it follows exactly without touching any obstacles. This is best robot for a kind of people. It is not easy to follow exact trajectory without any robot. This system shows a kind of application for blind people. Let's see other slide. This is other topic. We can use this kind of application, 6-legged robot. We use open dynamic engine. There are some references in robotic application. Wheel systems were not sufficient. We need to use legged robot because the surface sometimes is random. It is changing roughly, for example, with some ice or something like this. We should use wheeled robot, this kind of applications. We designed and this robot in real-time applications. This is also a control algorithm. We use open dynamic engine algorithm. This algorithm is a kind of equation solved for forward or inverse dynamics depending on the need. In this equation, we used Newton-Euler equations for following exact trajectory without touching any obstacles. Next slide, please. Yes, this is other references. The main problem is consumes more power than wheeled alternatives. Despite many improvements, the most efficient design are mature inspired robot, this kind of 6-leg robot. Next, please. Yes, as I mentioned before, wheel robot sometimes is not efficient because of roughness. We should use leg robot for this kind of applications. Next, please. Yes, this is, as I told before, this is our open dynamic engine. This algorithm, as I told, solved forward and inverse dynamic of robotics system. Next, please. Yes, this is a kind of block diagram or controller structure. It consists of mainly experimental robot, which has 6 legs. There is also a navigation controller, gate sequence controller. We should also support by time, because time is very important. It should be walk in a, as I mentioned, initial time. Servo motor controller and kinematic stabilization algorithm. And then stability is very important with this kind of working robot because it carries some loads because of roughness of lay. The position of the load is changing. We should use stability measurement sensors. Next, please. Yes, stability is very important for 6-leg robot. We use a kind of this algorithm. You can see on corner, it consists of 6 legs. There is also changeable center area position. Stability margin is nearest distance between the edge of the contact polygon and projection C1, G. In this result, the distance should be a kind of constant for this kind of walking situation. We try to keep the distance constant for this kind of stability algorithm. Next, please. Yes, you can see a graph. It shows the performance of criteria. This stability margin represent balancing quality of this kind of situations. And for this reason, we should provide some information about walking position of the robot. We also a kind of use numerical integral of time-dependent algorithm. And then this area error represents at the bottom of equation. Next, please. Yes, we tried to test our experimental robot for different size of steps. first step, you can see error margin. We also tried for 16 steps. You can see each step follows each other. And then the proposed margin is 6.39 error. But array error is also acceptable for this kind of application. Yes, this is our proposed robot, which consists of servo motor. It is nearly 12 servo motor, 6-legged. We also use this system Raspberry Pi, and then open dynamic engine based algorithm coded in the system. We also measurement IMU inertial measurement. We should measure inertia of each joint for this kind of robot because it consists of nearly 12 joints. It is not easy to control each joint because it is a very non-linear system. And then we use servo motors for each joints. Next, please. Yes, we can also use some sequencing of our 6-leg robot. I can use leg robot like this. We can choose some structure for this kind, for example, tripod, quadrupod, or pentapod structure. Can also see the sequence of the working of our 6-leg robot table. Especially this kind of structure has been selected because I mentioned before the surface of the road is very random. The working stage should adopt this kind of random structure. Yes, you can see some results, tripod, quadrupod, or pentapod structure. Velocity is also changing because of working condition of the 6-leg robot. For example, tripod is 10 millimeter per second, but pentapod is decreasing 3.33 millimeter per second. The result of experiment is seen that most stable moment has been made this kind of walking gait, especially quadrupod structure is a kind of acceptable walking condition. Yes, this tripod walking structure can see it is not random, it is a kind of sequence. It can be acceptable walking condition. There is also quadruped walking. This is in nearly 25 seconds. Is also good condition for this kind of robot. And there is other pentapod walking is easy. It is walking very roughness structure, but there is no very high peak for this kind of walking condition. Yes, this is other topic. There are many applications for crane system because carrying an object is very important in factories. We designed a 3-car crane system because it is not easy to carry like these bars or something like this. This structure is very reliable and good for carrying unexpected object in factories. Yes, you can see on the left side, we use 3 cars Initially, as I told before, the load structure is very different because center of mass is changing during the carrying. Because of this reason, we should use 3 cars for this kind of crane system. We also divided in 3 parts. Each cars has sensors. They are following each other with a constant distance. And then there is not big pendulum angles for this kind of structure. Let's mention about experimental system. The system consists of 0.37 kilowatt AC electric motor, 4 kilowatt AC electric motor, and 0.75 kilowatt electric motors. Consists of 3 motors. This is for moving on the right, left side, forward, backward, and lifting of the load. This kind of motors used. You can see the power of the motors are different from each other. We also use sensors. You can see experimental setup. At the bottom, the design of the system. At the top, the experimental setup. You can see bridge group on the color, carriage, and control panel, and proposed beam type load. And there is also a kind of data acquisition instrument card. We measure especially acceleration of the system, and then we use artificial neural networks to predict this kind of parameters. Yes, on the left side, the structure of the proposed artificial networks. It consists of 3 inputs and 5 outputs. On the right side, the block diagram of the system, we use accelerometer, sensor, data acquisition system, and proposed neural networks and the system. Yes, the table shows 2 types investigation on this experimental system. We use 1 car and 2 cars. We also change the load of cars. For example, 700 kilograms, 1,260 kilograms. The speed is same. Yes, there is other topic. We use a kind of industrial robot for randomly changing welding trajectory. This system consists of an industrial robot and welding system, and then there are metal sheets for joining each other with using different kind of cutting positions. Yes, this is our robot. The robot is a kind of QCAD, which consists of 6 degrees of freedom. It is a kind of real-time industrial robot. We use steel welding table and 20 steel metal pieces for experimental testing by using artificial networks. Yes, we can see the methodology of our applications. For example, we capture image and get clean image using image processing. And then we use neural predictor. Neural network predictor is generate to remove faults. And weld steam trajectory is planned. Position variables are we sent the robot. This is our sheets. Yes, these our sheets consist of a kind of step trajectory. As you can see from trajectory, it is position is changing suddenly. It is not easy to weld this kind of sheets by operators because there are some big errors joining each other, but robot when gets real information from artificial networks, it's welding without any errors. This is captured of picture, and then we are getting clean image, this kind of application, and then we are predicting this trajectory for robot, and robot is welding these two sheets. Yes, with errors, and after processing by using neural networks, you can see on the right side there is no random edge, this kind of welding position of the robot. Yes, we planned trajectory for robot. Robot is following this trajectory without any errors, and then welding quality is better than traditional operator welding structure. Yes, this is our neural network structure. Input consists input and two hidden layers. This is a kind of backpropagation training algorithm is used for adjusting weights of this kind of structure. Yes, this is a kind of experimental result. On the left side, without any process. On the right side, with artificial network results. Yes, this is our training performance of the proposed neural predictor. You can see very small errors. Yes, there is other applications. This is a kind of real-time application. As I mentioned before, there are many objects produced by CNC lathes. The shapes, the color, the material is very different. Because of this reason, we should use artificial system to predict and to give information to robot. Robot can pick up which object is good for the structure or which object is has fault or something like this. Yes, we used LabVIEW image processing system for LabVIEW, and then packing materials is Ottoman robot by using universal gripper. Gripper is different. Mainly this project is focused on a universal gripper. Three types of material are coming by conveyor, and then the material is determined by using this LabVIEW and image processing system. A robot is picking up which object is good or not. Yes, front panel of LabVIEW, and then the position of object. This information is going to give the robot. Robot is following the exact trajectory to pick up this kind of object. Yes, this is our experimental setup. This real-time robot, this small conveyor system, and camera and controller. Yes, we used some results. Two different methods has been used for this kind of classification, especially area collection and shape matching operations used by using LabVIEW and algorithm. You can see particle analyzer result. You can see position of the object, and the matching result is exactly the same by simulation results. Yes, information on the receipt of material is robot not enters camera image instead of digital signal. This is main focus on this kind of project. Okay, thank you for listening my presentation, and then thank you for attending my lecture. I am happy to answer your questions. Is there any questions?
Thank you very much, Professor, for your interesting presentation. I would like to remind that this presentation was focused on intelligent systems in manufacturing. It was really interesting. Is anybody has questions in conference room Poznan? I don't see questions in chat menu on YouTube. Okay, I have one question.
Yes, please.
As you know, artificial intelligence is deeply integrated into manufacturing systems. Let's assume, when will robots replace humans in manufacturing? Or is it a fiction?
Yes, there are many fiction films. In future, robots will be working as a worker in factories because robots has some superior performance rather than human being. There are many advantages such as the speed, the quality, responsibilities is better than human right. Because of this reason, in future, there are many intelligent robots can be used in factories for quality production.
Very much. Thank you very much for your time, for your sharing your recent research results. It's a great honor for us to host you online, virtually, during this conference, and we wish you a success in your future research results. Thank you very much.
Thank you very much. Regards from Turkey. I hope to see you next year face to face.
Thank you. Let's move to the next presentation. I'm happy to introduce the next speaker. Next speaker presents a company with 400 years history. Secotools is a worldwide manufacturing, and one more thing, Secotools is also pay significant attention to people capacity building. And I am pleased to introduce Dr. Vladimir Dolgich, who is a global course owner and trainer at Secotools. Dear Vladimir, nice to see you, and we are looking forward to an interesting presentation.
Hello, thank you, Vitaly. Can you hear me?
Yes, we are hearing you.
That's great. That's great. Thank you very much. Dear participants, hello, everyone. Greetings from Sweden. Finally, we've got some summer. Maybe you know, Swedes say that Swedish summer is 9 months of waiting and 3 months of regretting. So far it looks good. I'm really excited to join and being part of your nice conference, and I really appreciate for invitations, especially Professor Vitaly Ivanov. So today I'm going, by the way, can you share my screen, please? Because I'm sharing my screen and it would be much easier if you can. Is this okay for you? Of course. Okay, so Today, I'm going to present my company Secatools and outline what we are thinking today about metal cutting, and I think it would be also a nice connection to a previous speaker who is talking about robots and automation system. If you noticed, we have the name of our presentation is a people company in machining business. We still believe that people are a key important element of the whole chain of manufacturing, which is include, of course, automation and robots. So let's move on. I hope you have heard or seen this brand name Secatools. We are their Swedish company, which is presented in 75 countries today, and we have around 4,200 employees. And yes, if you will get any questions, please keep them up to end of this presentation, and that would be the most convenient way to communicate if you have something to ask. So, Secatools, the name Seca came from Latin language, which means I cut. We have quite interesting history. Our company started at Fagersta, Sweden, which is a little bit northwest compared to Stockholm, if you look to the map. I put on this slides main milestones of the development of the company, so you can see the roots. They went quite far to the history. So the first productions were started here rather far from now. And you know that Sweden is very well known for their iron industry, and probably you also know that their word tungsten, which is the wolfram, another name for wolfram. So the word tungsten means heavy stone in Swedish. So this is a nice and interesting connection between scientific and Swedish heritage. So here you see on the slide that in 1932, the separate production Secatools been initiated in 1974. We been part of their how we call this stock exchange in Sweden, and so on and so on. One of the way how companies growing is making acquisitions and mergers, and here on this slide you see some of those. We started in 80s with the company Carbaloy, which is US company who is famous, who's still famous on the US market. Then you can find other brand names here from France, like EPB, from Holland, Jabra Tools, AOB, Niagara. And the most interesting, I suppose, would be the latest acquisition which we have now, which been last year or this year. It's a Polish company, Fanar, who is producing solid round tools. So if you are familiar, you're welcome to visit this company. I suppose it's not so far from you. One of the points for marketing and technology were merged by initiating our logo. So you see this logo on the screen with nine squares and 9 boxes with different colors. And I'm sure you know that ISO standard split different materials, different workpiece materials by different categories. So here we see blue for steel, yellow for stainless steel, and red for cast iron. And also we saw that it would be great to split these colors also into 3 categories, like rough machining, medium machining, and finishing machining. So if you take any box of insert today or open our catalog, you can easily find what's the area, what's the purpose, how you can utilize this or that insert or a tool. So you can find a clear indication how it's supposed to be utilized. However, in year 2000, I add 3 extra categories of the materials, of the workpiece materials, which are now also included in the standard. This is non-ferrous materials, super alloys and titanium, and hardened steels. So today we extend our logo, and if you go to our catalog or the website, so we're going to talk about this just in a few minutes, you will find how easy and nice to recognize area of using specific tool. Few facts about us. As I said, we are presented in 75 countries. We have a lot of distributors, and of course, we have a few production units. As I mentioned before, the main production units located here in Sweden, in Fagersta, where we produce our inserts. However, except our inserts, you could imagine we need to produce some steel parts, cutter bodies, tool holders. We have a dedicated production for that in Arboga. We have one more company here, which is located in Norrköping, where we produce our drills. Also, we have other productions in other countries which are supported main production here. We also, for the whole world, we have 4 distribution centers, 1 for Europe, 1 for US, and 2 for Asia Pacific. And of course, we have a lot of customer centers which we use for multiple purposes, like education, providing different hubs, events, a lot of interesting activities. So pick up the nearest customer service center, and we also provide a lot of services today, which will be also in the end of this presentation. One slide to highlight that we also in trend, we're trying to be a sustainable business, and we align with the UN agenda. So there are many elements there, and we want to be on the top notch with the latest behaviors, with the latest way how to support our environment. As you might imagine, to produce tools, we need to create them, and creation is the core of research and development department, who is spending their time, efforts, experience, investigations to create new tools. Our main R&D center also located here in Fagersta. However, as soon as we have other productions and we have many different tools, we should have other R&D departments in different parts of the world. So totally today we have around 210 people in all R&D centers, which spend around 5% of their all turnover, which we earned during their financial period. And you see another interesting number here: more than 5% of R&D budget invested in intellectual property related matters. And to represent this, I have one special slide which represents duratomic coating. As you might imagine, that cemented carbide, the insert, is the heart of our production, and to protect its heart, we use special coating. And duratomic coating was so huge invention, which been launched in 2006, that after that you can see on this picture many inserts which been produced using this specific coating. I really like the slogan which been used for that time when this duratomic coating been presented to the market. We make the impossible possible, and that's really fantastic thing. So when the aluminum oxide coating become very tough and able to withstand dynamical forces. In the latest years, as you can see here, we also adjust the color of the coating, because in the beginning it was the black color, and now we have, as we call it, silver, which is more easy to use, because for operators, for our customers, it's much more easy to recognize their the toolware, the size and the pattern. Next few slides, I'm not going to stop on every single picture here, because otherwise we can spend days for investigating all these tools. I just want to highlight that results of investments, which I mentioned before, we got as many different tools and tool system which we utilize up to now. So as example here, we see their MiniMaster tool with interchangeable heads, which been invented in 1988, and we still use this system. We update the system, however, it still demonstrate that it's a valuable tool, and we can use it with really great results. Next interesting thing, which I also highlight, is this one, is STEP education, which means STEP is the the well-known word. However, this is also abbreviation, means Psychotechnical Education Program. As I said in the beginning, we claim that we're a people company, and to be that on that level, we need to educate our people, our partners, our customers, and keep this education on a high level. So we spend a lot of efforts and time for education. And one of the results of transformation of education is another point which I also highlight here, is the manufacturing transformation. So these days, nowadays, we see that the product itself is the great thing. However, service and manufacturing transformation way of working is even more important for our dear customers. And the latest point here, which I also really proud to introduce, is data metrics code, which been launched last year for the insert and tools. And I recently read news on our intranet that it's becoming more and more popular, and probably become even an industrial standard for the tools. Here again, I just want to highlight one of the points. A people company in the machine business, this is the one of the main important message which I want that you remember, because today, we don't know what's going to happen tomorrow, but today we think that people is the cornerstone of everything. As soon as people communicates to the people, people brings value. And we put these three statements. It's very important to have the right culture. Everyone supports other peers, and we of course empower our local expertise leaders. So what we have today in our portfolio? Today, if you open our catalog on the website or paper version, you can find around 30,000 products, standard products, which you can purchase really quickly. Today, as I said, we produce the whole chain from the insert up to the machine. We're not touching machines. We're really happy with our partners. So we produce inserts, tools, tool holders. And with this huge range of like 30,000 standard products, you also could imagine, just think, if we have 30,000 products, how many combinations you can create with this variety. By the way, do you know how many standard turning inserts you can find in our catalog? So just ISO standard inserts, we have around roughly 5,000 combinations. So to help our customers and partners recognize and be easy and fluent to work with this, we provide today a nice and a fantastic solution, which we call Suggest. Suggest, this is a self-service portlet, which you can find on our website, which has so many features, which has so many fantastic supporting functions. So I really encourage you to go there, and even if you don't need a tool, just play around this, because this is a fantastic way, this is a fantastic engine. A lot of scientific investigations and practical experiments lays behind this. And you can find the tool, you can find cutting parameters, you can find different strategies, you can adjust cutting parameters depending on the tool life which you want to achieve, etc., etc., etc. And today we also have a mobile version which we call Sec Assistant, and this is another way how you can get right parameters, right tool life. You can even here compare our products with our nice and great competitors. So you can make this comparison quite easy. And on top of this, as I said, we were still producing products because the product is the core, is the heart of our business. However, today we also provide a huge variety of services, which you can see here, like Innovations Hub. Innovation Hub is the unit where our specialists focus on a specific component or a specific area, such as aerospace or power generation, medical, whatever. They spend their time to produce a specially dedicated technology, pick up a specific tools to get maximum productivity or tool life, depending on what's the purpose of this research. We also have a recycling program because, you know, the cement and carbide is very raw material, and unfortunately it doesn't appear from the air. So we need to be careful with the resources which we utilize today. We have other services, as I mentioned, and you all can find all the services you can find on our website. So if you go there, you can find a lot of nice corners and areas and pages which are dedicated to different services or products which we produce. Also, I need to highlight that we also able to produce custom tools. So if our customers say, I went through a catalog and we didn't find something which is we really need, we as a company can listen to the customer and produce special custom products. And this is really fantastic area where our engineers demonstrate so great results and achievements. And again, if we're back to our services, our main part here is the manufacturing transformation, because this is their fantastic overview of the whole production from the beginning to end. And our specialists in consultancy, they are not just focusing on a small part of the chain like a tool. They can analyze, they can observe the manufacturing itself and provide a lot of nice, interesting ideas, hints, and tricks how to improve production as the whole thing. And again, addition to this manufacturing transformation, we spend a lot of energy for education. We work with different universities in different countries. We have different educational programs, online courses. We have fantastic library of books. Other services you can see here: engineering services, inventory management, machine monitoring. So it's a lot of nice things which you can utilize today, and you're welcome to contact our people in every country, or if you want, you can contact me if you need more details around the company and their services which we provide. Thank you very much. I really enjoyed to be a part of this session, and if you have any questions, or comments, you're welcome.
Thank you very much, Vladimir. I'm really happy that you find a time and deliver this presentation. I am happy that our graduates of Sumy State University achieve such heights and can share their experience not only with students but also with experts in manufacturing. Just a comment for all audience, this last December and this January we have together organized the online virtual program for our students and PhD students with the title Tool Materials for Manufacturing Technology, and it was really awesome experience because we learned a lot. Thank you very much, Vladimir, for you. Thank you very much for your contribution to conference, and looking forward for cooperating with you in the future.
Thank you, Vitaly, for invitation and for being part of this nice, great audience and participants. Thank you.
Very much. Okay, next speaker will come from Greece, and I'm happy to introduce him. The research laser-based additive manufacturing with a subtitle Long Arbitrary Path Simulation is Real-Time and Power Optimization. This presentation will be delivered as a video presentation, but Professor George Christopher Wozniakas is online and he will be ready to ask your questions or comments after this presentation. Just a few words. Professor Wozniakas is a well-known scientist in manufacturing engineering. He is in the top of 2% of scientists worldwide, and his experience is recognized internationally. He's a director of Manufacturing Technology Laboratory of the National Technical University of Athens in Greece, and I'm happy to start this presentation. I'm asking a technical assistant to start video presentation of Professor Wozniakas.
Hello, my name is George Wozniakos. I'm Professor of Manufacturing Systems. Hello, my name is George Wozniakos. I'm Professor of Manufacturing Systems at the National Technical University of Athens, and I'm going to give you an account of our work during the last 10 years on laser-based additive manufacturing, in particular on long arbitrary path simulation in quasi-real time, and followed by power optimization. A few words first about our lab. Manufacturing Technology Lab at the National Technical University of Athens. You can see on the map where we are located, and obviously in Athens, in Manufacturing Technology Lab deals with manufacturing processes, with engineering materials, with machine tools, and of course with manufacturing systems. We've conducted about 27 research projects with EU and Greek funding so far, and we do approximately 5 to 7 projects per year with external company funding. There are 5 faculty members in the lab, 2 technical staff, 1 administrative member of staff, 5 postdocs, 20 doctoral students at the moment, and about 30 master thesis students or final year students per year on the average. Our infrastructure, a building of around 3,200 square meters in area at 3 levels, more than 45 machine tools, metrology and materials testing, and a number of PCs, more than 30 actually, a lot of CAD, CAM, KS software packages, and you can see more information in our web page, web portal I would say, mtl.mec.nt. Let me go directly to my lecture. The lecture is based on 3 papers which we published with my collaborator Emmanuel Statatos between 2018 or 19 and today. And it's about selective laser sintering and melting. Today, SLS SLM is the main representative of precision additive manufacturing, where the laser follows a path on powder layer, and it's basically a thermal process, as you I'm sure know. A number of advantages, like a wide range of materials, like complex geometry which can be achieved, and of course this is an industry 4 technology, and some disadvantages as well. Amongst them, high build time still and cost, high cost, non-standard part quality, and lack of process parameter optimization in the last 30 years at least, of a serious approach that can realistically simulate and optimize long paths. And this is exactly what we try to do in this work. Now, the trends in simulation optimization of SLS and SLM today, the first observation is that the process should be modeled and regarded in multiple scales, at the powder level, at the bead level, at the layer level, and at the part level, each one being restricted to a particular scale, where we talk about either mechanisms or the baseline modeling, or basically temperature fields, and finally at the part level, stress and strain fields. The multiple granularity of these models spans microscopic, mesoscopic, and macroscopic levels, and the tools that are appropriate there differ, as you can see, and the time that is necessary for running such models also differs a lot. Now, what is required is basically new simulation tools and new abstraction techniques. We found out that this is the main trend actually towards new simulation tools and new abstraction techniques, and this is what we followed as well. Now, the optimization is realistic as opposed to just simulation. It's realistic up to the layer level, not up to the part level with good results, at least so far. Optimization of temperature profiles is mainly targeted, and the path topology should be considered, but is not actually considered so far to an appropriate extent. there's a need for fast computations, which basically stems from the fact that simulations, that a number of simulation runs should be executed, and that's why, in order to optimize, to find an optimum result, and that means simulations should be fast. The trend is towards machine learning because of speed, clearly, because of orders of magnitude of faster execution compared to just numerical models, to finite element, for example, models. Now, our approach is a threefold approach, I would say. The parent simulation model is the first model that we construct. It's based on macrophysics, and it targets the bid level. Temperature and density prediction are also the main targets of this model, and this is based on automated data production, batch production of a lot of data, because this is necessary for the next model. Our next model is basically a surrogate simulation model, which tries to make the most out of batch simulations in order to predict temperature and density. It uses random paths, and it tackles random paths, which is quite good. And it operates at the layer level. That means 100 meters or more of path. And it's definitely more efficient than the parent simulation model by orders of magnitude. The last model I'm going to present, today, is the power optimization meta model, which is based on the surrogate simulation model. That's an extension of that. And then it tries to optimize laser power so that constant, or as near as constant, temperature can be achieved along the full path. Properties are also, mechanical properties and so on, are also kept at a desirably constant level. A few words first about the parent simulation model. This is a finite element model, basically. It's a thermal model. It's conducted in ANSYS, and it's a moving heat source model. The heat source moves on powder layer. A Gaussian distribution of heat flux is adopted, which looks like this. And the thermal simulation should proceed more or less like this example that I show here, with the temperature curves following the movement of the beam. It should have enhanced computational efficiency, and we achieved that by using thermal shells rather than 3D elements, by gradual mesh coarsening, by tweaking ANSYS numerical solution techniques after having understood their essence, and we conduct batch simulations, and we do that by fully parameterizing the model and then producing data results in. Now, the material, the powder material, is modeled basically through the relative density that it exhibits, which is the density compared to the bulk density. That ranges between 0.5 and 1. And its thermal conductivity, K, may be modeled according to one of the three different laws that I can show you here. Of course, thermal conductivity is a function of relative density. The relationship between thermal conductivity and temperature is established through density, actually. And we end up with definition of a number of virtual materials in ANSYS. And in fact, the material evolves from its initial state to the final dense state by changing through this different or scanning different virtual material modes according to temperature change, of course. In technical detail, we compared both solid and shell elements, and we found out the combination of shells and selective reform strategy for activating them and for material evolution was the best. We use the mesh in different modes in 3 different regions: dense, less dense, and normal, I would say, WT and F regions, we call them in this figure. Now, the thermal history that was recorded either experimentally or numerically in other people's works, we used it in order to validate our own results, the thermal history that we predicted. And as you can see here, with this first work, Yin's work, we did quite well. And also we did that in 2 orders of magnitude faster computation time. Using Kolosov's very well-known benchmark, we also had good results. This one is interesting because it's experimental results. It concerns experimental results. And also we used a model that was developed and run on a supercomputer in the States, Kairalas model, Kairala and Anderson. We used, of course, different modeling techniques. They used discrete element modeling. We used finite elements. But look at the comparison between their CPU time and our CPU time, which was minuscule. The results were very comparable, actually, as you can see in this figure. The full colored areas are Kairala's predictions, and the curves, just the boundary curves, they were our predictions. They were quite close. Now, a few words about our second model. You saw, or I suppose you are convinced now that our simulation model is accurate and is very fast. Now, how do we use it in order to produce a surrogate simulation model to improve on speed of execution? We use a machine learning paradigm, machine learning model philosophy, where we replace the physics-based simulation model by artificial neural networks. Of course, these do not solve differential equations. That's why they are very fast, even for a layer level. What we try to do is to predict the maximum temperature first, and after we do that, then we go with prediction of density. We also put special emphasis on the path, because this is critical since it dictates thermal accumulation on the layer, on the powder layer. And the key that enables us to take into account the path is path decomposition and modeling by a few parameters. So we don't use standard geometry, but only a few numbers in order to represent any path. We use as benchmark case this austenitic stainless steel powder 316L with scanning speeds about 1 meter per second, beam radius quite small, 50 microns. We use a step size for discretization of the path equal to 2.5 microns, and the laser thickness the layer thickness of the powder is 25 microns. The original path descriptor, which I want to briefly present to you, is what you see here. So you can see a random path in blue, and then you can see a number of circles, which are the descriptor's domain, which follow the beam. They are concentric to the beam, and while the thing is moving, some path part of the path turns red, and this is the previous path. So it's the history of the consolidated powder, and you can see that gradually the whole of the path becomes red because it's history now. Now, we discretize the path, as I said, with certain step to 12.5 microns. We consider the current point of the path, which is where the beam is, and by red color we denote the past path, and the blue color is the future segments of the path. Now we define a number of rings of increasing diameter, and according to these rings we define a vector which has a number of elements. Each element contains the number of past points that is within the respective ring. So if we had 10 rings, we would have 10 elements in the descriptor path. Now, what we want to do is to model the memory, the thermal memory, basically, of this system. So any past segment may be found close to the current point where the beam is, and the older this past segment, the colder it becomes, or the lower its temperature is in the evolution. Now, we use an upper limit in the number of past steps that should be considered. So we don't consider all the past steps, all the past history of a point. And you can say that there is long-term memory where the global shape is considered, and there's short memory where just parts or this limit applies, or parts of the evolution. Now, how large this short memory should be is a matter of regulation, and it's a matter of each individual ring. And this kind of regulation, we do it by trying different values while the actual artificial neural network is built. So we do at the same time both the construction of the neural network by training, and also the trying out of different memory, basically memory values, so that we do a global, you would say, optimization of both the topology of the neural network and the parameters describing the path description. Now, in terms of implementation of the neural network, this uses as inputs the descriptor vector and some internal temperature feedback. That's temperature that's calculated by the neural network, and it's fed back into itself. Now, the final output of the network is the maximum temperature, as I said, at each point of the path, not at one point, at each point, discretized point on the path. We used a training set of 450 random walks of length 1.5 millimeters each, and that required 3.75 CPU hours on the parent model, the simulation with finite elements. Then we started training the ANN conservatively by 10 rings and 9 hidden neurons in the neural network. What I have to point out here is that the rings do not have random diameters, but the radii or diameters are connected according to this Fibonacci sequence. Those of you who are familiar with mathematics know what the Fibonacci sequence is. For example, in this case, 1, 1, 2, 3, 5 multiplied by the path step, which is 12.5 microns, is the radius of the first, the second, the third, and so on rings. Then we used fine-tuning of both the rings and memory. That means that their number and the memory, the number of points that each covers, is adjusted at the same time while training the network. Now, the generalization of the neural network, we did it not with short paths, but with long paths for better validated results. It turned out that the best architecture after systematic evaluation, trial and error of ANNs gave a root mean square error for training and generalization, both about 10 degrees Celsius, which is quite good considering the hundreds of degrees that are necessary for melting this kind of material. So you can see here the scanning of the path, and at the same time it's the execution of the ANN actually. At the same time, the maximum temperature that is recorded at each point of the path while this is scanned by the laser beam. And you can see the vectors while they are changing, the memory that the rings encounter while this scanning is done. Now we did some improvements to increase speeds. For example, in any case, the ANN was 100 times faster than the parent, for at least for relatively short paths, 20 millimeter paths, but we improved that further by splitting the ANN into two ANNs. Actually, this is quite technical, but I would like you to have a look at that. It's the pilot ANN, which is basically the same as the existing ANN, but without temperature feedback. It's based on path topology only, and it predicts temperature for the whole path. And then this is followed by the master ANN, which is actually the existing ANN, but it's parallel working. Starts from the pilot ANN temperature estimation, and this is what makes parallelization possible. So it's parallel computation, and at the same time, we should consider that this works as an iterative improvement of predictions. So this master ANN does work by iterating up to 10 times and improving like that the results, which was quite tolerable. So you can see the results of these iterations for an initial curve that was first recorded. Then depending on the iterations, we have better and better results, hence the different colors of the temperature evolution curves. Further improvements were based on the calculation of distances which were necessary at the beginning. We needed to improve by making this static distance calculation more efficient, and we used KD trees to do that. Quite an improvement. And then we used rider, we called it, rider ANN for relative density calculation. That is, the density was predicted in the same way as temperature, but by a different artificial neural network. The RMSE of this network was quite low as well, so we believed it and we're happy with the result. A statistical validation was done for this case for about 100 random paths, relatively short, and this statistical validation gave us confidence that such results, where you can see the path, and you can see the temperature, and you can see the density at the bottom, were quite close to what we would obtain by the simulation, the finite element simulation model. So we're quite happy with it. And indicative results for other types of paths, as you can see here. This is a comparison basically between finite elements and artificial neural network. You cannot see the difference because there is not much difference actually. The two curves are quite close to each other. And you can see also an execution for curved paths, which is quite possible to do here. And at the bottom you can see, of course, the result in terms of maximum temperature that is computed by the artificial neural network for this particular curved path. the time performance, which was quite good. I have a table here for you to have a look at for different types of paths, trajectories, starting with Hilbert curves and going to hatches. We did the simulation in quasi-real time, as you can see in the third and fourth column, and the final fraction of real time. The simulation time ranges from 2 to 63 seconds, and that's about half the time that the process actually takes if we wanted to run it in reality. So that's why we call it a real-time simulation through ANNs. You can see some numbers here. For example, for the square space filling exercise that this table represents, 2200 square millimeters area, path length of 5 to 132 meters, and linear time increase as a result with path length. Calculation time in less than 50% of the actual process. And let me say a few words finally about the third model, the meta model for power optimization. It's an enhancement of the surrogate model by adding laser power to the inputs at constant speed, of course. We didn't play with speed, we just assumed constant speed. The challenge was basically the training of the ANN. We used two training sets, one for 350 random walks with constant power, which were randomly selected in a given range. The power was within 50 to 150 watts. And then another 350 random walks with random variable power. Variable power in terms of probability of random variation of the power at each step. So that was quite general, quite generic, I would say. The paths were short paths of length of 1.65 millimeters, 6 straight segments of 75 microns before possible turns, and then but these turns were stochastic basically. 8-hour simulation time of the parent model was required in order to generate the data to train the ANN, which was quite reasonable, I would say. The root mean square error for the training was about 31 degrees, and the generalization about 32 degrees, which was quite good given the melting point of this steel materials. And this is the kind of result that you get. So you have similar curves to the ones that we got before, but the idea is that we want the temperature to remain constant and not fluctuate. So for the temperature to remain constant, we do need power optimization. The power meta model simulates the path with nominal power by parallel working, and temperature profile is read, and then an adaptive law is applied for correction of the power profile in order to make the temperature more constant, more and more constant. The adaptive control law is of that type, of the exponential, well, square type, I would say. So it's reverse correction of temperatures, basically. It's applicable to the entire path, and it's done at once. It's a vector operation, that's why it's very fast, and iterates until no substantial correction is required anymore. That is, until temperature is more or less constant. That happens after 3 to 7 iterations for an allowable deviation of temperature of 5%, and of course more iterations for a smaller deviation. So you can see how much improvement is achieved by fluctuating, well, varying the power in order to achieve more and more constant temperature. You can see it more clearly here. You can see that the temperature is almost flat, a flat curve at the end after the initial wide variation of temperature, and at the bottom you can see the variation of power that is required in order to achieve this flat temperature. The side of the square, the total path length and the optimization time for different cases of space filling is depicted here. You can see quite, I would say, reasonable optimization time in terms of conclusions. Main contribution and outlook. Parent finite element models, performance from temperature and density data, data generation for any path, and we used it in the surrogate simulation model, which handles the infinite dimensionality of random paths quite fine, I would say, and it does very fast simulation for practical paths, which is something that's very rarely seen in literature. The final power optimization model, that's fast optimization of power profile through iterative mode for full path at once, which is the vector operation that I mentioned, which is quite promising, I would say. The outlook, basically consider laser speeds and thermomechanical fields, expand from layer to the part level with suitable 3D descriptors, optimization alternatives. This is used, for example, reinforcement learning or deep learning, convolutional networks, and so on. Thanks very much for your attention.
Okay, dear participants, close mine. Dear participants, just now was a presentation delivered by Professor George Christopher Wozniakos from National Technical University of Athens. As you can hear and as you can see, it was a laser-based additive manufacturing, non-arbitrary path simulation in real time and power optimization. In my opinion, this presentation was really interesting and needed, and it was well structured and well presented. If you have any comments, questions, please ask them. Professor Wozniakos is now online and will respond to them. As I can see, Professor Dobrotvorsky in Poznan University of Technology is ready to ask a question.
Dear Professor, maybe I don't understand. You use what type of laser you use? It's continuous or pulse laser? And what parameter, if you use pulse laser, what parameter of your laser? Value length, time of impulse, energy in impulse.
Thank you very much for your question. Can you hear me?
Yes.
Yes.
Great. Okay, that is really not relevant because we developed a simulation model that can deal with any laser, because we see lasers basically as a source of energy delivery. So it may be pulsed, it may be continuous, it may have different power, and so on. We're able to simulate any type of energy delivery. So in some of the examples I used, it was a pulsed laser, but it could be anything else. The emphasis is actually not on the type of laser or the actual implementation, I would say, of the laser system, but on the simulation, provided that we regard all lasers as sources of heat input. We model the laser as a moving heat source, and that's it.
I think it's not possible. I think it's very important when how short you take a laser impulse.
Of course, but we can do that. This is what I'm saying. We can model any laser pulse formation or configuration. This is what I'm saying, because it's only simulation, isn't it?
I think if we use maybe a short, maybe nano
very
laser,
short.
maybe femto laser, you need study maybe two temperature model when we have only a high level of electron and not high level ion. Its mechanism of temperature is another. When we have big laser impulse and when short, I think you need to attention your view on this problem.
True, femtosecond we didn't try. That's true. What our benchmarks or the cases that we tried were purely from literature because we wanted to compare our results that came from machine learning methods to literature, documented cases in literature. So this is what we did. We did not perform any experiments at all.
Okay. And another question. You use ANSYS, and have you any your own program? Another program?
No, but it's not necessary because ANSYS is very powerful and it allows us to build our own routines, and we did that a lot on top of ANSYS. So we modified some of the routines that ANSYS uses, for example, for activating different materials or for providing the transition from one density or to another. So different densities basically mean different materials, and different conductivities as well mean different materials. And ANSYS allows us to do that. The main problem we had was that of efficiency, because shell elements were more efficient, but they did not allow us to use the full temperature profile across the thickness of the element. So we had to admit that the full thickness of the elements had the same temperature, which is not true in practice. But because they were shell elements, because they were thin enough, we were happy with this sort of hypothesis, or we said, okay, we at the gain of much faster simulation, we would be happy to neglect the difference in temperature distribution across the thickness of the elements.
Okay. Thank you very much.
Thank you for your very nice questions.
Thank you very much for questions. Thank you very much for answers. Any other questions? I think not. Thank you very much, Professor, for your contribution to conference. It was very nice to see you and listen. Just interesting presentation.
It was my pleasure. It was my pleasure. Thanks very much.
Looking forward to meeting you again in person in SUMI, maybe when it will be safe.
Hopefully. Thank you very much again.
Thank you very much. Now our agenda is completed for this session, and I must admit that now is a break for lunch, and we will return to broadcast in 2:30 by Polish time, GMT +2. So time for lunch, and looking forward to meeting you in 1 hour and 20 minutes.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Znajdujemy się w laboratorium modelowania inteligentnych systemów produkcyjnych. To jest laboratorium, które zagląda w przyszłość. Myśmy przenieśli część przemysłu na Politechnikę. Dzięki temu możemy realizować prace badawcze i eksperymentalne, tak jakbyśmy je robili w środowisku przemysłowym. Jeżeli chodzi o oprogramowanie, w dużej mierze jest to przyszłość, która też jest przedmiotem zainteresowania firm software'owych. Jesteśmy w stanie przeprowadzać szkolenia związane z wybranymi obszarami automatyzacji bądź przemysłu 4.0 i to jest ten ważny element, który staramy się wykorzystać również w tych działaniach związanych z zarówno współpracą pomiędzy uczelniami, jak i współpracą z przemysłem.
Co to jest?
Co?
No to!
To? A, to. Przycisk do papieru. Zbudowałem wczoraj.
Ale to trzyma pranie.
No.
We'll teach you how to build robots, and you do what you like with it. Faculty of Mechanical Engineering, Poznan University of Technology. You create your own future. Mechanical Engineering, for those who want to know how things work and how they are made. Mechatronics, for those who want to bring mechanics to life. Biomedical Engineering, for those who want to develop modern technologies in medicine. Production Management and Engineering, for those who want to be leaders and managers of production processes. Join us and start creating the future. Faculty of Mechanical Engineering, Poznan University of Technology.
Welcome in the session titled Smart and Sustainable Manufacturing. We have to change the order of presentation. The first speaker will be Marta Popowska from Poznan University of Technology with the paper titled ADD Methodology for Solving Problems in the Production of PVC Pipes. Marta, floor is yours.
Thank you very much. Good afternoon. My name is Marta Popowska, and it's an honor to be here and be able to give my presentation before you all today. Title of my presentation is the use of the 8D methodology in solving problems in the production on PVC pipes. My co-authors are Natalia Marzec and Justyna Trojanowska. So now I would like to begin with introduction. As everyone knows, the main purpose of existence of manufacturing companies is to make profits, but satisfying the needs of customers. Due to ever-increasing expectations, companies have to constantly evolve and adapt to change in the market. Going on next slide. According to the Lean transformation framework, problem solving is an integral part of a lean organization, and the ability to solve a problem is essential to achieving its strategic goals. At each stage of the problem solving process, certain tools are used, such as Ishikawa diagram, process map, Pareto diagram, or priority matrix. The ability to properly implement these methods positively affects the effectiveness of the developed situations. Our research project was conducted at the PVC pipe manufacturing department. All products are manufactured from PVC compound by extrusion process. And the scheme of extrusion line of pipes are on this slide. Now I want to go to the main problem and research task. The research aim is adjustment of pipe diameter thickness. And our research task, first we made identification of waste in the company. And during the observation, we noticed a problem that involved setting the thickness of the pipe diameter. The problem created waste and increasing the startup line of the excursion line. Startup time, I'm sorry, of the excursion line. Then we analyzed data of amount of waste generated and prepared a chart covering 8 months based on data from ERP system, which showed that the problem is obtaining the wrong wall thickness of the pipe. Now we can move on to the research methodology. We based on the concept of lean management. We decided to apply the 8D methodology to solve the problem. We extended to the original 8D methodology through our original steps. And the original steps of the 8D methodology you can see on blue, while the added steps in yellow. So starting from step zero, we analyzed the data to confirm the significance of the problem and found that the problem occurred in every month from January to August. The next step, build a team. To build a team, we analyze the task performed by each person in the process and appoint a team of 9 people. Step 2 is describe the problem. We get information directly from the place where the problem occurred. Step 3, define the goal. Define the goal. To that end, we held a meeting with our entire team where we develop a common goal and discuss the 8D methodology because we wanted to everybody know how the 8D methodology works. Step 4, secure the customer. Our problem doesn't negatively affect the customer because quality control checks each pipe before delivering it to the customer. And step 5, find possible causes. So in order to find all probable causes of the problem, we made an Ishikawa diagram, and this diagram you can see on this slide. Now we can move to 6th step, find possible solution. We held a meeting with our whole team to find solution to the problem, and brainstorming was used to find corrective ideas. And our ideas also you can see here on this slide. Step 7 is develop a sequence of implementation of solution. In order to make it easier for us, we decided to make purity matrix, and in that way we choose the best option for us. After analyzing all the ideas to solve the problem, it was decided to implement solution 7. It's a measuring tool, and the Gantt schedule was created with deadlines and people responsible for specific actions. And step 8, the next one, is develop the plan on implementation and perform corrective action. And here you can see our action. First, we design of a tool, then manufacturing, testing, and in the end, we wanted to implement it to other manufacturing lines. So the last steps are steps 9, assess to effectiveness of corrective action, prevent recurrence of the problem, and the last one, express appreciation to the team. So now time for results. On this slide, you can see the amount of the waste caused by the pure pipe wall thickness has fallen from 14.7% to 2.1%. And time spent on adjusting the head gap related to the total startup time from 24% to 7.5%. So it's more than our target was. So now to sum up, time for conclusion. Here you can also see the difference in results before and after on the graph. And now it's time for conclusion. The problem has been eliminated through implementation of an original methodology based on the classic 8D methodology. As a result of implementation of the solution, waste generated in the excursion of pipe for home sewage system caused by a broke thickness of the pipe wall has been reduced by 12.6%. And also duration of the process of adjustment of the excursion head gap during the startup of the line has been shortened by 16.5%. So thank you very much for your attention. Here is a contact to me. Thank you.
Thank you very much, Marta. I think we can move question session for the coffee break. And now it's time for the next presentation. It will be Leon Cetik from University of Zagreb.
Good morning, everyone. My name is Leon Cetik and welcome to my presentation. First of all, I would like to thank my associates Dragan Perakovic, Ivan Svitić, and Marko Periša. The topic we are discussing about is cybersecurity validation in the online gambling industry. In the introduction, we will discuss about information security, digitalization of the online gambling industry, and the penetration testing. Information security is essential in organizations because it offers confidentiality, availability, and integrity of data and systems necessary for safe operation. With the development of technology, the number of cyber attacks on computer systems is increasing. To avoid unwanted events, it is necessary to protect the system with certain security aspects. The digitalization of the online gambling industry strongly contributes to the growth in the innovations and offers all forms of gambling, making it part of a more comprehensive concept of Industry 4.0. In the past couple of years, the players have been attracted to online betting, live betting, online casinos, and online lottery games, either through the offer of such gambling games on personal computers or smartphones. Significant progress in online gambling has been observed during the COVID pandemic and numerous lockdowns worldwide. So it's very important to protect organizations from cyber attacks by developing both external and internal security environment. One of approaches is penetration testing, where security expert is placed in the role of attacker to find security vulnerabilities and threats within the system. In addition to existing knowledge, experience, tools, and methodology, the penetration tester tries to find system vulnerabilities such as unauthorized access to the system and data, disabling the system or obtaining the privileges needed to control the system. For this work, we established cybersecurity validation methodology applicable in the online gambling sector and present practical part using penetration testing methodology in vulnerable environment. The perimeter of performing penetration testing depends from client to client, as do the procedures, methods, and tools used in testing. There are different requirements that organization may request from pen tester, depending on their information and system security needs. The need for organization to conduct penetration testing may be aimed at protecting the financial sector, protecting personal and critical data, preventing system protection, or enforcing protection against an already committed cyber attack. Various companies, organizations, and entities have a great need to protect their information system. Most of them are not aware, sufficiently informed, or do not know the quality protection of actual complex communication structures and have a little or almost no control over them. On this slide, we can see two graphs. The first one shows gross gambling revenue, online and offline in Europe from 2003 to 2023. As we can see, the total revenue increased in the last couple of years, mostly because of increasing an online gambling caused by COVID pandemic. In addition, other graph shows the frequency of cyber attacks on different organizations. Data from 2018 show that the riskiest are government organizations, which in 90% of cases are the target of attackers. Along with government organizations, 90% of attacks are suffered by various multiple industries. The target of attacks on government organization is mainly for the purpose of obtaining sensitive information without authorization, while in the most other organizations, the most common causes of attacks are financial. On this slide, we will discuss about classification of information system threats. Every organization classifies information to identify potential threats affecting their system, so they can protect themselves by implementing security systems using hybrid protection techniques. Smaller organizations can plan on one or two threat classification criteria. For example, smaller organizations do not have to do full protection of the internal system with few employees, while larger organizations must identify all sources of threats to protect their system on the highest level. Classification allows an organization to identify threats that affect their assets so they can protect them in advance. Quality approach can enable the construction of security systems or help to create hybrid protection techniques by analyzing a combination of different classification of threats. The actors in the implementation of threats are people, natural disasters, and technological impacts. According to research published in Computer Crime, the highest percentage of risk to organization is caused by the human factor in the internal part of the network. To prevent this threat, it is necessary to introduce educational measures to employees. Natural disasters are caused by earthquakes, fires, storms, or wars and terroristic attacks. Technological threats are caused by a physical or chemical process over equipment and other system assets. A penetration testing methodology is the manner in which a penetration test is organized and executed. Penetration testing methodologies exist to identify security vulnerabilities in organization. In next slides, I will show you methodology used in online gambling penetration test. Penetration testing process is divided into 5 phases: collecting information, network mapping, vulnerability identification, exploitation of vulnerability, and documentation. The first step is collecting data, what will be a key process in further testing. There are plenty of methods used to get target system data, including Google search, while web page source code analysis is another technique to get more information about the system, software, and plugin versions. There are an array of free tools and services available in the market to provide information like database, table names, software versions, and hardware used by various third-party plugins. We use network mapping to discover physical and virtual connectivity. Most often, this step we use automated tools such as Nmap or Zenmap to get information about the network. After we scan a whole network, we have to identify vulnerabilities and determine their level and type. The level of vulnerability determines order of exploitation that will be used. After identifying vulnerabilities, we start with exploitation, which is the most important part of performing penetration testing. We have to exploit vulnerabilities to take control of the system and, if possible, do privilege escalation to extend access to the entire system. Some of most common attacks in cybersecurity are man-in-the-middle, malware exploitation, phishing, password cracking, SQL injection, cross-site scripting, denial of service, and zero-day exploit. If vulnerability exploitation phase did not aim to access the system, for example using DDoS attack or slow loris attack, then attack vectors are implemented automatically. After we used all of exploitation, we can finish our penetration test and report all knowledges about the system. In this section, I will show you practical part of this work. Goal of practical part is get root access from vulnerable system by following penetration testing methodology applicable in the online gambling sector. First of all, we have to manually collect information about the system. It's very important to find as many as possible information about the system, so the penetration test can be quality performed and cover all possible vulnerabilities. By collecting information from system, we can see that website use the HTTP protocol, which means that the site is not encrypted and it will be easier to carry out penetration testing attacks. Also, we can see from the website a login form that can be potentially used to perform SQL injection or password cracking to gain access. Using the View Page Source option, it is possible to access the source code of page and take information about website. Source code results show us that this website contains Joomla open source web content management system, which can potentially be used to exploit vulnerabilities of system. After we collect all data about system, we have to identify vulnerabilities that can be exploited. For scanning a network, we use Nmap tool, and result show us open ports 22, 80, and 3306 with SSH, HTTP, and MySQL services. Another tool we use for this stage is Deerbuster. The result collected by Deerbuster tool shows several directories on the server that need to be explored. Analyzing one of the directories, we access the website login page. Individual vulnerabilities were found using searchsploit Joomla and OpenSSH versions. The results show us how Joomla version is vulnerable to SQL injection and cross-site scripting. By retrieving the document for additional explanation of SQL, we were suggested to use SQL map tool to perform automated SQL injection attack. The primary and the most demanding phase of penetration testing is exploitation of vulnerabilities. The first attempt to exploit the vulnerability is performed using the SQL map tool to conduct SQL injection attacks over the Joomla version. After exploiting the SQL injection attack, 5 databases were found, and after analyzing each of them, it was determined that the Joomla database is vulnerable. The information granted to access the website administrator is a username Jonah and a hash password that needs to be cracked by finding the appropriate format. After seeing the form, it is necessary to break the hash record with the help of the John the Ripper tool. After collecting credentials for access to the website administrator, it is necessary to set up and run a reverse shell to gain remote access to the system. After joining the system, it is essential to gain privilege escalation, which is achieved using a line script that finds the necessary credentials to access greater authority. After accessing a greater level user, it is required to run command sudo l, which shows command ran as a root. Taking advantage of the wrong configuration and running the code make it possible to achieve root privileges, which completes the practical part of the work. In the last chapter, we will repeat all the most important findings. Also, it will be suggested few security measures to implement in vulnerable system we previously tested. We have to know that neither system is secure, but we still have to improve security measures to set risk to minimum. The practical part was successfully performed and found vulnerabilities that allowed remote access to system. Vulnerabilities that lead to successful penetration tests are collecting information using source code, network mapping using Nmap tool, finding hidden directories using Deerbuster tool, identifying vulnerabilities using searchploit, exploitation system using SQL injection attack for getting credentials, using arbitrary code for performing privilege escalation which lead us to the root privileges. After testing, examiner offered organization a report and suggestion for resolving security vulnerabilities. The system vulnerability was caused by incorrect configuration and incomplete system updates. Various vulnerability solutions are provided through better firewall configuration, access control methods, the latest software version, and protecting against SQL injection attacks using input checking. Also, it is recommended to upgrade web application with SSL protocol and set it up to redirect traffic to a secure HTTPS protocol automatically. Statistics in this paper show that most interest group of cyber attacks are organizations of great importance, such as online gambling, and that's why preventive mechanisms like penetration testings are required. Penetration tests require professionals to use their knowledge and simulate an attack to protect information system. Thank you for your attention. I hope you found this presentation useful. In case of any additional questions, feel free to contact us on email. We will be happy to answer your questions. Best regards to everyone.
Thank you for your presentation. I had one question for you, but I understand that you prefer to send it by email, so I will do it. I would like to ask how the COVID affected the development of this market, but I will send this question via email. Now I invite Wacław Masek from University of West Bohemia.
Okay, hello everybody. My name is Václav Mašek. I'm a PhD student at the University of West Bohemia, and my presentation is about assistant rider system, driver system with visualization in rider's view. So let's go for it. Yes. In Czech Republic, annually, there are more than 100,000 traffic accidents where more than 500 people are killed. And motorcycle riders are one of the most vulnerable parts of the traffic because they have more than 30 times less chance to survive the accident. And on the other hand, the 6 times higher chance to get involved into accident by the same amount of registered vehicles. So we started to thought about that with using the appropriate assistance system, we can reduce those numbers. Let's go to the research tasks. We started to conducting the literature review and find out that there are very small amount of the possible assistance system that rider can use. Most of the currently available solutions has only information, can only provide the information. So we wanted to specify the features of what suitable assistance system can have. And we started to develop an assistance system which is relatively cheap, can be available for everybody, and use commercially available hardware and the software attached to it. So we don't have to spend a lot of time with the first prototype development. We used engineering, design science, and methodology for specifying the key features of the system. The first prototype is not optimized for injection molding. We thought about 3D printing because we wanted to change the dimension to appropriately pose all the sensors. As I said, we wanted to use commercially available hardware. We don't wanted to spend time to invent our own, but of course in future the things can change. And we use the software which is based on this hardware. So we use the libraries provided by the manufacturers which can accelerate the design process. Yes, we use engineering, design, and science methodology for finding the best solution. We presented three possible solutions. First is that combine visor and sensors in one device, but the solution is quite heavy and don't allow to aim the sensors appropriately. Back, please. Back. Yes. The second solution uses sensors attached to the front fork of the vehicle, and place them above the light. But our motorcycle doesn't allow the sensors to be attached there, so we decided to use third solution, where the sensors are attached on the front fork, on the suspended part of the front fork, and the visor is on the rider's helmet. We also presented two types of attachments of the sensory unit on the front fork, and we decided on the right one because it protects the sensors and the computing board better than the first solution. And we also presented two versions of displaying unit, and we choose the right one again because the second one, even though it allows better view because it protects the combiner from the sunlight, there is less field of view on the right side, so the rider can't see the vehicle appropriately when it comes from the right side. We also made a sensor specification which is necessary, and software specification and application. When we go to the system architecture, first we get it, on the picture, the red lines are for the energy flow, and the blue lines are for the signal flow. So we start by acquiring data from the sensors. We use GPS and inertial unit for speed determination, LiDAR or infrared sensor for measuring the distance from the front vehicle, and camera for traffic sign recognition and pedestrian recognition. Then we compute everything which is needed in Raspberry Pi, which is the main computer of the sensor unit, and the main computer of the displaying unit, which is currently ESP32, just shows the pictograms and warnings according what the Raspberry Pi computes. So it's not so computational power demanding. And both boards are communicating using Bluetooth interface, and the signals are displayed by using two displays. Yeah, we use infrared. As I said, we use the infrared sensor for measuring the distance from previous vehicle, accelerometer, and GPS sensor for independent speed measuring, and camera for traffic sign recognition and pedestrian recognition. This camera also has a night vision mode, which we currently don't use. Yes. Yeah, to size. Yes. And let's move to results. So there you can see the final designs of the displaying and measurement and sensor unit. We tested our algorithms for sensor fusion, which independently it can make up to 80 measurements per second, but combined with image processing, it goes down to several measurements per second. So probably there's a need for improvement in the future. And we used hard cascade classifier for traffic sign and pedestrian recognition, but we decided to make our own datasets in the future because our currently used datasets are not good enough. Yes, and we also can improve the communication speed because so far we are on probably 3 communication steps per second, which allow us only limited visualization of the warnings. Yeah, here you can see the placement of the sensors of the sensor unit. There are infrared sensor combined with camera in the front part. There is placement of the inertial unit and GPS inside of the sensor unit. And there's placement of all electronic parts of the displaying unit that you can see in the blue square. The rest of the unit is just the power source. We used the combiner without collimatic optics, which is sufficient enough for displaying the warnings, and it saves a lot of resources. And we also made several analyses, both mechanical and ergonomical. Output of the image processing algorithm during the testing. Yes. Yeah. Okay. So, and we also tested the displaying hardware. As you can see, the displays are bad enough for future development. Okay. So we made design study of the ergonomically acceptable system, which allows real-time image processing and sensor fusion, and warns the rider using pictograms. Yeah, there are several references, and the project is free.
Thank you very much for interesting presentation. Stay with us, please.
Yes.
We have time for one short question. Do you have any questions? I can see also questions via internet. So maybe one short question from me. It was really very interesting presentation, but what's your idea for further research in this area?
Yeah. Of course, we have to improve our algorithm to make it faster and more durable, and also improve mechanical design mainly. We already broadened our team by the expert which is expert in electronic spooling. So it allows us to make the whole device smaller because we can cool it more efficient.
Okay. So good luck.
Thank you very much.
And the last presentation in this session, it will be Dmytro Adamenko from Germany.
So, welcome also from my side, and welcome to my presentation concerning the topic of smart retrofit of existing old plants and machines. This research has been carried out as I was still the employee of the University of Essen, and if the one observes the industry, the production industry, then that is actually the very traditionally strong industrial sector, and it's coming into enormous cost pressure in the last time because both manufacturers and operators of the plants and machines are trying to minimize their costs, and also the manufacturers have normally a zero margin if they sell a machine and gain the profit actually from the maintenance. So the maintenance is becoming the biggest cost-saving potential both for the manufacturer and operator, and this is something which is trying to be solved by gaining the data about the current operation process to get insights with the development of Industry 4.0 in the machine, and also to get the state of the machine detailed. This should offer the possibility to recognize the early equipment or machine failure, and when the new modern machine is being delivered to a customer, normally it already has all of the new modern sensors and processing equipment, but the older machines, which are actually fully intact and full in use and could normally operate for several more decades, they don't have this possibility and they don't have this technology, and then they cannot gain a profit from it. Move to the next slide, please. Okay. So the one possible solution could be the smart retrofitting, where the company tries to add the new sensors, new sensor processing equipment, and mountings to the existing machines in order to optimize its production. So the problem which comes up when the retrofitting the whole shop floor, that normally one company or one shop floor has a very heterogeneous machine park, and they are also normally very different. There are many highly specific components with highly specific applications and a lot of physical values one can measure. And no one normally can say what value should be measured actually, and if there is one physical value known, it can happen that it cannot be measured within one's application. And also one consistent throughout holistic process was not established. Therefore, it was a research task to develop such a method for the holistic retrofit process, which would be transferable and suitable for most of the active working plants and machines, which would get a benefit or be a high potential in this holistic process. We could save the time for maintenance, for example, where the critical parts should be pre-ordered. We can save the cost where the mounting parts or spare parts should be standardized, and also increase the quality of the produced products. Okay. So the proposed retrofit method contains 3 milestones within it. It's highly iterative, so we can move backwards in the process, and also the catalog of the sensor hardware and sensor mountings should be provided at the end of the project. And in the first milestone, it should be carried out or defined whether the machine should be retrofitted or not. Therefore, one had to estimate the current operating costs of the machine, to define the cost which would be spent within the predictive maintenance. The investment cost should be also obtained, and the basis for the decision making should be created. If the decision is positive and the machine should be retrofitted, then we have to define what the critical components are. You can whether look at the documentation and see how the machine has operated in the history, or you can try the knowledge-based method to select these critical components. After the critical components are known, the values to be measured should also be defined. And the last step would be the acquisition of the actual condition of the machine, because normally none of them is as delivered for several decades ago, but has some new features or equipment installed. The suitable sensors should be selected, as well as suitable mounts. I will go in detail in the 3 of these sub-processes, and we'll start with the definition of measured valuables or measuring selection process. In this case, or in this step, the critical parts are already known. Therefore, we start to analyze the possible load states. The possible load states for mechanical loads have been derived from the catalogs of Kohler and Kastrup for elementary functions, and for every of the mechanical load state, a characteristic physical value which can cause a failure in this state has been selected. Otherwise, for every of the load state, besides this characteristical mechanical value, the further physical values have been derived or found. So we can switch from one physical value to another if the needed one is not measurable. And so is also this benchmark matrix developed, so we can see if the desired value is not to be measured, if we can switch to another one. After we decided what we actually want to measure, we have to select the sensor somehow. And there are no method suitable for sensor selection for existing old machinery known, but the ones which are dealing with the sensor selection for the new machines, they have a key challenge, which is measurement disturbances for certain physical values or physical processes. And till now, there is no method for tackling these measurement disturbances proposed. And within our method, we try to classify the possible physical measurement principles to define the disturbances which can spoil this measurement task, and classify this sensor selection. So if we have as an input a measured value installation space where we can mount our sensor and the ambient condition, we can select the value we are measuring. We have the requirements and characteristics of the measurement. We can derive the disturbances from there, add the requirements for safety and signal quality, and then we have the filtered sensor selection. For the sensor mounting design process, we tried to define the possible mounts for as many plants and machines as possible, and also to develop a catalog of it. For this method, we have proposed a synthesis of the mounting based on an active area coupling method, and the variation according to specification of rod. So we can, for every coupling, define or distinguish the suitable coupling by type, form, position, size, and amount, and also use commercial mountings as a basis for further development and as a basis for catalog development. In the method has been, the holistic method has been validated within a retrofit project of a wind turbine. It has been with the company PE Concepts. It was 800 kilowatt Enercon wind turbine in Germany, and the tower was selected by the experts as a critical part. Also, the measuring points within or on the tower have been defined by the experts, and the remaining useful life of the tower must be continuously calculated by acquiring the process data and describing its current state. In the next step, the measurement should be selected, and most important value for remaining useful life calculation of the tower is actually the force which is generated by the wind blowing into the blades of the turbine. And wind force can also be used or causes the tower bending and extension calculations, but it could not be measured directly. The value should be expressed through the other physical values. And as a possibility, or as a proposal, the tower was presumed as one Bernoulli beam clamped at the bottom, and the extracted physical values from the benchmark matrix have been derived, and that could be acceleration, vibration frequency of the tower, and the tower extension. So the acceleration, wind acceleration, was defined as a main characteristic physical value, and tower extension, sorry, actually as a check value. The last part, or almost last part, was the sensor selection. So disturbance values have been derived after the measurement selection. It have been light, the humidity, noise, vibration, air pressure, and changing environmental condition around the wind turbine. So sensor for wind acceleration, wind speed, hub rotation, frequency, tower extension, and power generation have been selected with this method. The development sensor catalog has been filtered according to the process presented before, and all the selected sensors were suitable to perform the measuring tasks after the talks with the experts. And in cases of rotation frequency and wind acceleration, alternative measurement principles found out by the method have been proven, where the experts first didn't think it would go so, it would work this way. And for the mounting design, the suitable mountings have been found in the created catalog. The parameters they were fully parameterized, and the parameters of the reference part were adjusted. So the retrofitting was performed by standard commercial mounting parts. So the holistic sense, as a summary and outlook, the holistic sensor retrofit method was introduced and has been validated by retrofitting the wind turbine. Now it is also validated by a package conveyor, or by retrofitting the package conveyor. The transferability of the method to other machines or plants types should be further evaluated, and the catalogs for sensors, hardware, and mounting should be further developed and actually held up to date to go with the technology, to develop with the technology. That will be everything from my side. Thank you very much for your attention.
Thank you very much. We have 2 minutes for questions. Do you have any questions? And can you come, Mas?
I properly understand you that you have a difficulty and characterizing the wind force, yes?
Yes.
In analytical approach.
Not analytical. We simply want to measure it. The mathematical calculation model was not our part, but our problem was how do we get the force? And we didn't get the force directly. We get it through the Newton.
You mean how you apply such boundary conditions to this? Or you are talking about the measuring of this force?
We didn't measure it. We came through the wind acceleration. So we use the Newton law F m multiple a and get it derive it from the wind acceleration.
Listen, maybe the plastic approach is the best idea to analyze such because in this case you can apply the mean value of this force and just identify or maybe get the some deviations in which this line can change. So in this case, you will maybe solve this problem.
Thank you very much. We relied also on the expertise of our partners of PE Concepts, which are developing the wind towers and serving them, maintaining them. So it was also a mutual decision. But thank you very much.
Okay, thank you very much for your presentation. Thank you for participating in this session. Now we have 10 minutes of technical break, and I invite you in 20 to 4 Polish time for the next session. Thank you very much.
Dear participants, welcome to the session second, Manufacturing Technology. During this session, we have 5 presentations, and maximal expected time for each of presentation is 15 minutes. Of course, it would take a shorter time, it would be very good. Okay, the first presentation is entitled Influence of Multi-Pin Ultrasonic Impact Treatment on Micro-Relief Structure and Residual Stress of AISI-O2 tool steel, and it will be presented by Mr. Dmytro Lesik. Please come, Mr. Dmytro.
Good afternoon, dear participants. Today I'm going to present a research about influence of multi-pin ultrasonic impact treatment on micro-relief structure and residual stress of AISI-O2 to steel. This work was conducted in collaboration with Kurdumov Institute for Metal Physics of the National Academy of Science of Ukraine and Al-Balqa Applied University from Jordan. Also, I present West Pomeranian University of Technology, in which I started my postdoc recently. So, I would like also to say a couple of words about my university. The Igor Sikorsky Kyiv Polytechnic Institute is public technological university located in Kyiv. On this slide, you can review the main building of our university. The university has 16 faculties, 11 educational and research institutions, and several research centers. It trains about 25,000 students, postgraduate and doctorates. So, mechanical surface treatment such as shot peening, deep rolling, ultrasonic shot peening, or ultrasonic impact treatment, ultrasonic finishing, laser shock peening, or hammer peening, usually applied to induce compressive residual stresses in the near surface and provide nanostructuralization to provide grain improvement in the near surface layers. And so the peening treatments are effective and low cost solutions for surface modification and of metal parts. Therefore, the improvement of surface peening processes in terms of reducing the surface roughness is an urgent task in the mechanical engineering industry. And the research aim of this study to estimate the effect of multi-pin ultrasonic impact treatment on the surface properties of tool steels under optimized parameters. The mechanically controlled ultrasonic impact treatment is one of the advanced mechanical surface treatment. It should also be noted that ultrasonic peening technique is characterized by low cost and can be referred to as green technology. And the research tasks are the following on this work. We focus on studying the near surface structure, hardness, residual stresses, surface texture, and also roughness and waviness parameters. So studied steel is often used where of expense of high carbon and chromium tool steels would not be justified. The chemical composition of studied steel is presented in table. Also, you can see the surface texture and profile of polished piece specimens. The average roughness was about 0.6 micrometers, and surface hardness was about 8 Rockwell value. Ultrasonic impact treatment was implemented using multi-pin head. The used equipment consisted of ultrasonic generator power output of 300 watt and a frequency of 21.6 kilohertz, an ultrasonic vibration system with piezoceramic transducer and step-like horn. The scheme of the ultrasonic finishing and hardening process is presented on this slide. Also, you can see ultrasonic tracks on the right of this slide. To optimize the ultrasonic processing parameters, experimental design was implemented. The vibration amplitude of ultrasonic horn was varied in the range of 15 and 18 micrometers. At the same time, the treatment duration was from 60 to 240 seconds. The response variables were evaluated using linear or quadratic regression models. The microstructure of the studied steel is mainly consisted of perlite nature and vanadium carbides. Based on the XRD analysis and TEM observation, the severe surface plastic deformation by ultrasonic impact treatment leads to grain refinement in the subsurface layer. Taking into account the treatment duration, the grain size of 180 nanometers can be achieved at the treatment duration of about 150 seconds and vibration amplitude of 18 micrometers. The hardening depth of studied steel was about 90 micrometers. You can see on this image presented on the right. Next, please. The maximum Rockwell hardness value were observed after ultrasonic treatment at the vibration amplitude of 19 micrometers and treatment duration of 180 seconds. However, you can see further increase in treatment duration leads to decrease of surface hardness due to the overstraining of the near surface layer. This result also correlate well with the literature data. The most remarkable increase in the surface intensity was observed after pinning treatment and 102 seconds and 180 seconds. Next, please. So the compressive residual macro stresses are formed regardless of the ultrasonic parameters applied. In contrast to the treatment duration parameters, increasing the vibration amplitude led to a slight increase in the residual stress values. Compared to the initial state, ultrasonic impact treatment provides a new way with surface micro-relief, and as compared to the initial state, the maximum height is lower after ultrasonic treatment. Please. The observation shows that the smallest of the roughness parameter can be achieved by the ultrasonic processing for 120 seconds at the ultrasonic amplitude of 19 and 70 micrometers. Compared to the untreated state, the application of ultrasonic treatment causes a significant increase in the surface waveness parameters that can be provided the lubrication conditions. So on this slide, you can see design solution for optimized level, and it should be noted that the experimental values are very close to each other, providing the error magnitude is less than 5%. So the main conclusions are the following. The ultrasonic impact treatment parameters were narrowed using experimental design. The applied technique leads to the increment surface hardness by about 50% and as a reduction in surface roughness by about 50%, providing the hardening depth of about 90 micrometers and grade size of about 300 nanometers, and the compressor residual stress of about 650 megapascal in the subsurface layer. Thank you very much for your attention.
Very much for your presentation, very synthetic and valuable. Okay, I'm starting the discussion. Please ask the questions. Come closer to the microphone. Sorry.
In your research, you use LEED, low energy diffraction, electron diffraction. I see. What information you have from this method?
Diffraction? You mean XRD or
low
energy transmission electron microscopy?
LEED. I see on. Okay.
The transmission electron microscopy was done to estimate grain size in the more high level.
Which?
The previous slide. So there is the optical, there's a structure, light.
Yeah. Yes. It's a low diffraction of electron.
Yeah.
Yes. But
diffraction.
You have monocrystal or not? Material. I see. It's traditional steel, but this method is for monocrystallish very well. What information for me very interested what information you take from LEED on your.
I only at the moment can say you if our diffraction in the cycle it's give us signal that our grain size is reduced, and we have grain and fine size here as compared to the
maybe in your steel we created monocrystal surface. Okay.
No problem.
Thank you. Okay, thank you very much for the question. Are any questions from the internet? Any questions from the internet? Okay. So once again, thank you very much for your presentation. Okay, the next presentation is entitled Improvement of the Milling Effectiveness by Application of Composite Milling Heads, and it will be presented by Ms. Julia Denisenko. Please come here.
Good afternoon. I am Yulia Denisenko. Sorry. So, good afternoon. I'm Yulia Denisenko, and I present the Department of Manufacturing Engineering, Machines and Tools, which is part of the Faculty of Technical System and Energy Efficiency Technology. Stop this. And Sumy State University is situated near the Russian border, and but our political situation don't stop our activity at educational process, cooperation, and research work. We have graduated students at 3 study programs: applied mechanics, industrial engineering, metrology, and informational measuring equipment. Our cooperation has repeat development with more than 15 partner universities from European Union and not only. And our research directions, you can see, and at the slide, we deal with development of and design the fixtures, technological process, cutting tools and molds, and we have research in standardization, in development of regulations, harmonization of standards, quality measurement, management, sorry, in production process and tool provisioning, and etc. And today I want to present the first our direction, and it's well known that rotation of flat surfaces may carried out by well-known methods. For example, face milling, plane milling, flat broaching. Face milling is more productive, but when we speak about large-sized workpieces, when the width of cutting more than width of tool, some difficulties may arise. For example, we need to do more runs. That's why our research aim is to increase the effectiveness of milling large-size workpieces by developing a composite milling head containing 3-phase mills and providing symmetric regulation of the milling width. For researching this research aim, we proposed the composite milling head that allows milling in one pass. It consists of 3-phase mills with spindle carrier. These phase mills are may rotation for the angle what we need, and this rotation is via spindle carrier of our milling head. And we may fix the angle by fixation of angular position. Face milling of a surface with width B is performed in the fit directions DS. The spindle carrier of milling head contains 3 mills of diameter D mill, and the indexing of the spindle carrier by the angle alpha can be carried out of the range of 0 degrees till 360 degrees. But as we understand that the minimum value of operational width is the diameter of one face mill, its position of 90 degrees, and it increased to maximum value to approximately 3 diameters of face mills. This position is 0 degrees or 180 degrees. This figure shows a diagram of symmetric milling width by angle alpha, and we may see the direction of rotation in the right side of this scheme. It's counterclockwise, and indexing of the spindle carrier may be an angle alpha from 19 to 180 degrees. But we have cases that we need to index our spindle carrier from 0 to 19. For example, when we milling the groove bottom plane. Next slide, please. This slide shows the possible variants of the proposed composite milling head. We see this variance it depends on the angle of indexing, and we calculated the dependence of the operational milling with mills with a diameter 315 millimeters, and we calculated how the operational width will depend on the angle. Next slide, please. Next slide, please. Also, we calculated the effectiveness of the suggested composite milling heads, and the effectiveness increased to 2.7 or 2.9 times. It depends on the diameter of our mills. Please. So conclusions. First, we propose the new approach. We propose a new type of milling head. We calculated the operational width, which depends in diameter of milling and depend of angle of position, and the operational width is varies in the range of 315 935 millimeters, and authors calculated the effectiveness that increases our effectiveness with our milling heads up to 2.7, 2.9 times. Next slide, please. And the scientific results have been partially obtained within the research projects, which ordered by the Ministry of Education and Science of Ukraine. One of these projects is within the joint Ukrainian-Slovak Research and Design projects. This research was partially supported by Research and Educational Center for Industrial Engineering, Sumy State University, and International Association for Technological Development and Innovations. And my own acknowledgements to our colleagues. I will try. From Poznan University of Technology is Dr. Justina Trainovska, Professor Olaf Chizak, Kielce University of Technology, Dr. Vladimir Lushinsky, and Rzeszów University of Technology, Professor Katarzyna Antosz. from Poznan University of Technology. It's not complete list from person who care of us. So thank you very much from not from only me, from all Ukrainian people who live near with me, for our safe lives, for your care. Thank you very much. Thank you for attention.
Thank you very much for the presentation and these nice words. It was very emotional. I know that the situation is as it is, so.
Thank you for all Polish people, because Poland really, and all European Union, but Poland is most of all.
Thank you very much. Okay, so we can start now the discussion. Please ask the questions. So I have one very short question, because the title is the composite milling head. And it means that this milling head was made of composite materials, or it was related to the construction of the milling heads, which are not one, are three.
Yes, the second one. Yes,
the
yes.
title for me from the beginning was a little bit misleading, because we have monolithic tools made of ceramics, for example, in case of milling tools. So I thought that it is some kind of composite which is right here applied. And next thing is this is only now a project. This is not a practical experiment yet. Only simulations. Right now.
With 3 million heads is a project, but we have experience with 2 million heads.
Okay, but you did not present any experimental research.
Yes, yes, we will do it next hour.
Okay. So
Conference.
Fingers crossed. Thank you once again very much.
Thank you very much.
The next presentation is entitled A Special Feature of Turbine Blade Deformation During Machining, and it will be presented by Mr. Sergei Dobrotvorsky. Please come here.
Dear colleague. One time.
Hi.
Okay. 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 I thank you for attention on this conference. I very excited in my speech, but maybe I start. Today we have started a new Horizon program. Please, new Horizon program in Europe. Very huge focus on clean transport. This is especially true for aviation. In aviation, we have two big problems. It's clean, it's pollution, air, and noise. But in this program, pollution is lost with high водорodic energy, but noise is a problem. No. In air, we have engine. It's more a contribution in the formation of noise. In most beautiful, most impact. It's natural or loading frequencies in blades. Next, да. Okay. And we decide to take a research by modeling. To the aim of the work was to study the influence of the condition of fixing blade in the device during the finishing machining of change its natural vibration frequencies. Our goal tasks, this is a comparison of the oscillation parameters in the blade when it's fixed in fixture, in device, and herringbone type lock. This is dovetail type. Therefore, is attached to this is like is turbine or maybe on compressor disk. Next. Oh, research methodology. We use two way. We created an analytical models and then solution in MATCAD and creation of 3D model of the blade subjects modeling and study by definite element method of stress, strain, natural and forces vibration. Yes. In the analytical method, the deformation on the plate was considered taking into account the angle of twist and moment, as well as internal loads. Next. The schema of fixing and boundary condition are presented on this slide. Next. And analysis was made for distribution of stresses and deviation or deflections during machining. On the left, we have stress. On the right, we have deformation. Next. On the left, we have clamping. On the right, we have clamping in dovetail, like in this turbine. When we have frequency model number 1, we have maybe this small but many more frequency. But in general, process test same like on the vice on dovetail. Next. Maybe in the second model and third model frequency, we have the same parameter. Next. But we don't have the same in another region. Only first three model we have maybe the same. In another models, not the same. It is to 20,000 of hertz when we heard with our next. In oscillation frequency model 5 and another, we have local deformation and local frequency. It's very very hard information to understanding maybe, but it's really we in this region we have local deformation and local frequency. Next. More information we have from frequency of cumulative effective mass participation factor from Planck and Dovetale. Only this region we have the same. Another problem. So local. Next. Mass participation of normalization clamping in Weiss and clamping in Dovetale. We see the same three position. And local position on another frequency. In the end, we take defense of deflection and stress in the magnitude of the load in our experiment. And okay, in short conclusion, the proposed analytical model can only use to estimate the limiting deviation in the plate with accuracy maybe 15%. The critical frequency of transverse vibration of the blade with the maximum amplitude are mainly in the low frequency region of spectrum. Clamping in the Weiss allows you shift the vibration process towards higher frequency is almost half the vibration amplitude. This can provide better processing quality and lower noise level. Okay, next. The fact of correlation of low frequency vibration models under different conditions of the fixing may indicate the presence of technological heredity in the distribution of natural vibration frequencies at various stages of manufacturing. With an increase in the frequencies of natural oscillation, the role of form oscillation in the blade increases significantly. Local deformation in these places will require a local change in processing parameters. However, no one modern CAM program are not yet capability of this. It's also obvious that new requirements for the level of pollution and noise will affect both the design and process technology of blades and other engine elements. And I hope to the end of Europa Horizon program in 25, we will overcome this problem. We have time.
Please ask the questions. Okay, please come closer.
We study stainless steel for turbine, classical turbine blade.
Any other questions? So I have one very short question. The subject is very interesting because it correlates the clamping conditions during the machining process with the vibrations which can occur during the process. And you have, based on this FEM simulation, yes, you have obtained that two different types of clamping can have the effect on the natural frequency and its modes, yes, of the turbine blade. Okay, but for me, it would be very interesting to carry out some experiments in the, for example, rotational speed are passing frequencies, which will be equal to the natural frequencies in order to validate this method. I think so.
Yeah. In work before this, we study milling process and load from milling, and we study when we have frequency when frequency from mill is in another
similar to the natural frequency.
Similar. But when we in this when we do local deformation, I think in our new research we demonstrate a new strategy to milling in when we maybe lost this problem. Really, we have this information, but it's in next
presentation.
Next
Because it
presentation.
will be very interesting for me to see these results. Yeah.
It's maybe it's no secret. We need take trajectory when we have ISO line of deformation. It's very new.
Because the distribution of natural frequencies are variable along the turbine surface. Yes. So okay.
Always program can program. Now work about form without special deformation.
But it was 3-axis milling, yes?
Yes.
Okay.
Yes.
Okay. Thank you very much, Professor. Thank you once again for your presentation. The next presentation is entitled An Analytical and Experimental Study of the Grinding Process of Thermal Barrier Coatings with Highly Porous Wheels of Cubic Boron Nitrate. And it will be presented by Ms. Tatiana Chumachenko. Please come here. Okay, you will be the speaker. Please come here. Okay. Yeah. This is not my loss.
Only because of the technical reasons, not about the rhetorical.
At first, I won't say that February. How to At first, I want to say that February is a fatal month for both for our country because of the war and for the Department of Material Science of Odessa Polytechnic. Professor Lebedev Vladimir Georgievich died in February. He was a very talented and intelligent person. We miss him very much. Today's report is devoted to one of the latest topics, which was led by Vladimir Georgievich. And the main theme of this topic is an analytical and experimental study of the grinding process of thermal barrier coating with highly porous wheels of cubic boron nitride. Next slide. Introduction and major challenges. Thermal barrier coating are widely used to protect heat-resistant alloys from high-temperature oxidation. Three basic requirements are imposed on thermal barrier coating: low thermal diffusivity, resistance to cracking and high temperatures, and increase and service life. Most fully meets these requirements thermal barrier coating of zirconium oxide. Zirconia-based ceramics are highly durable and crack resistant. Ingredient thermal barrier coating high contact temperatures rise, the values of which are comparable to operating temperatures or slightly higher than this. At present, CBN grinding with highly porous grinding wheels has become quite widespread. When grinding with such wheels, it should be borne in mind that initially the contact of CBN grain in a unit volume of the CBN alloy is much lower than that of wheels of the number 6 structure, which correspond to ordinary CBN wheels. Next slide. Aim and research task. Silicon-based ceramics are highly durable and crack resistant. In the grinding process, high contact temperatures arise, which are comparable to operating temperatures or slightly higher than these temperatures. The task in the design of the grinding process is primarily to control the thermal treatment mode, to maintain within such limits that the residual stresses have values that don't pose a danger to the durability of the sprayed wire. In addition, if the contact temperature of grinding research 1200 degrees Celsius in the sintering of the sprayed wire begins, leading to the loss of thermal barrier properties. Next slide. Research methodology. The research aimed primarily at studying the grinding forces, grinding temperatures, and the establishing patterns of heat field propagation in the thermal barrier wire. Immediate attention was paid to obtain the dependencies of the change in the temperature field on the most significant possible number of factors of the grinding process. So varied processing modes, grain of wheels, and the supplied coolant effect. Next slide. Features of grinding these highly porous wheels are what the ratio per unit volume of grains are porous is significantly increased in favor of porous. This means that the number of achieved cutting grains per unit surface of the CBN wheels is significantly reduced. From this, it follows that the allowance is removed with a smaller number of grains compared to the wheels of porosity 6. Furthermore, each grain removed a larger chip and the higher unit cutting forces can be expected during processing. Next slide. The total cutting forces PZ are slightly reduced. This is because the number of cutting grains in the contact batch is reduced, even though unit forces are slightly higher. An increase in unit forces from each grain can compensate for a decrease in the number of cutting grains in the contact spot. An increase in unit cutting forces PY can an increase in temporary stresses. So under the above grinding condition, temporary stresses for 6 to 6244 megapascals, for structure 26 to 6635 megapascals, and structure from 40 to 6755 megapascals. Thus, temporary stresses increase. The values of temporary stresses are significantly higher than the comparative strength of zirconium oxide. Such stresses should cause cracks in the sanding wire, but as indicated, crack don't develop due to the porosity of the sprayed wire. You can see on table 3. Next slide. Unit cutting forces are slightly greater than grinding these highly porous wheels. This suggests that the cutting temperatures of single grain will be slightly higher compared to the temperatures that occur when grinding these wheels of structure 6. Considering that practically all thermal barrier coating are non-conductive, the method of artificial thermocouple is applied. One electrode is a steel foil and a contact foil is used as the second electrode. The foil sheets thickness from 6 to 20 microns and the distance between them is of the order of 40 microns or less, depending on the thickness of the capacion paper, which insulates them from each other. For a stable formation of the thermal junction, the thermal electrodes are annealed at a temperature of 1000 to 1100 degrees Celsius for 30 minutes. The ends are brought to the surface and welded together during grinding. As a result, a thermal spike with a thickness of 2 or 3 microns appears, and through a thermocouple of iron constant type is formed, which was very low inertia. Mathematical modeling has confirmed this assumption, as the results are shown in Table 4 on slide 6 and Figure 1 on slide 7. Analyzing the results can conclude that the unit temperature of cutting grain during grinding these highly porous wheels is slightly high. A contact temperature measurement using micro thermocouples confirm this assumption. Slide 9. Oh, 8. Contact temperatures sustain residual stresses. In the case of grinding these highly porous wheels, the walls covering the formation of residual stresses are the same as when grinding these ordinary wheels. Since the contact temperature is lower, the stresses are also lower when grinding these ordinary wheels. Generally, grinding these highly porous CBN wheels can increase the limiting processing condition by from 15 to 20%. The most effective contact grinding temperature can be reduced by feeding mineral oil or water-based coolant to the contact zone. Modeling of such grinding conditions showed that a decrease in the temperature could result up to 35 or 30%, which naturally makes it possible to tighten grinding modes. In particular, significantly, it is possible to switch to high-speed grinding without fear of causing defects on the thermal barrier wire. On Figure 9, on slide 8. Slide 9. It is rather difficult to simulate the roughness value for a wall. The roughness state was estimated indirectly by the magnitude of the grain depending in the material and by direct measuring. The results of the comparative analysis are shown in Figure 3. As can be seen from the above graphs, the magnitude of the dependent of the grain in the material for highly porous wheels is from 10 to 13% more. So we can expect an increase in roughness by first category. Next slide. Results. It was found as a result of mathematical modeling of the CBN grinding of thermal barrier coating zirconium oxide. Depending on the processing condition, the values of the cutting force component PY can reach values of the order of 20 newtons. The values of the component of the cutting force PZ can reach values of 10 newtons. Cutting forces don't cause temporary stresses that could lead to cracks in sprayed zirconium oxide wire. Then grinding these highly porous CBN 26 and 30 wheels, the unit cutting forces are from 15 to 20% higher, and the total cutting forces are from 7 to 10% lower. Contact temperatures are from 10 to 15% lower when grinding these highly porous wheels. Calculations carried out according to the developed mathematical model show that under sufficiently increased grinding conditions with highly porous CBN wheels, the grinding temperature is in the range below 1100 degrees Celsius. This temperature level excludes the surface sprayed oil sectoring and decreasing in its thermal barrier properties. The thermal stresses during grinding of pure zirconium oxide and stabilized this yttrium oxide by ordinary CBN dose are highly porous, 3,700 to 4,400 megapascals. In some cases, the stress exceeds the compressive strength. However, due to the porosity of the spread oil, the crack doesn't develop by depth. Residual stresses arising under the influence of contact temperatures on the surface during grinding of pure zirconium oxide. A stabilized zirconium oxide, this yttrium oxide, these wheels of ordinary porosity and highly porous wheels reach significant values of the order of 60 megapascals. However, these values are much lower than the tensile strength of the thermal barrier wire and don't lead to crack, naturally within the framework of the study's processing regimes. Then grinding these highly porous wheels an increase in roughness by first category can be expected. Then grinding these highly porous BN wheels, grinding conditions can be increased by from 20 to 25%. All experimental data were obtained under careful dressing of the CBN wheels. For avoid, it is recommended to avoid salting during operation. It can cause thermal defects on the grinded surfaces. Conclusion, next slide. The purpose of the work to determine the optimal condition for grinding thermal barrier coating this highly porous CBN dose has been mainly achieved. Grinding this highly porous CBN dose of zirconium oxide thermal barrier coating makes it possible to obtain good results than grinding without putting signs of surface, often slightly cooled by blowing air through the pores of the wheel under very intense processing conditions. Since the surface roughness increases somewhat, it is necessary to provide nursing passes. Then construction of the operation, then unit forces are minimal and the roughness can be reduced. Then designing the process of grinding the thermal barrier coating, it is recommended to use the data in tables 1 to 3 and 4 and figures 1 to 3. Next slide. Thank you very much for your attention.
Thank you very much for the presentation. Now I am starting the discussion. Please ask the questions, but I think that you can stay with us because the discussion is a very important part of the presentation because this is some kind of exchange of scientific ideas. Yeah. Okay. Do you have any questions?
Always discuss on.
Okay. I have one question, but maybe we will leave it for later time. Okay. The last presentation entitled "The Effect of Manufacturing Tolerances on the Hydrodynamic Characteristics of Plain Bearings," and it will be presented by Julia Tarasewicz. Please come here.
I can start, yes. So good evening, colleagues. First of all, I'd like to express the big thanks for organizers, for the SUME organizers as well as the Poznan organizers, because it's very important in such difficult circumstances have such a possibility just to not only to change the scientific ideas and solutions, but just to know that we are not alone and we can have some help and understanding from the other people. And greetings to the SUME University and colleagues who are in the seminar. I think you will be safe and everything will finish very soon. So best regards for you. And the title of my presentation, firstly, maybe I should say that I present the University of Science and Technology, Krakow, and this work was carried out with cooperation of some state university, Evgen Savchenko, and the topic of our research was the effect of manufacturing tolerances on the hydrodynamic characteristics of plane bearings. And the next slide, please. Could you sometimes, yes, because I make the presentation just to. So, modern machinery, no matter how complex and sophisticated it is still mostly operates with the simplest and the oldest type of the bearing. And these bearings are usually called plain bearing or journal bearings. And the plane bearing is nothing more than just a shaft which is rotated in the stationary sleeve. And despite of the such simply design and construction, the theory and the operation as well of such units are very complicated. And first of all, it should be noticed that the plane bearings are running under different lubrication modes. Firstly, when shaft is stationary, there is no enough lubricant to separate the two parts completely. That's why in a startup stage, these bearings are running under the boundary lubrication mode, but when the shaft starts to rotate, the liquid lubricant is involved into the cone shape of the gap, and it generates extra pressure, which just effect on the bearing capacity. And then the speed of the rotation of the shaft is sufficient. Then the full film lubrication is generated, and the surfaces of the shaft and the sleeve are separated completely. And this is the best way and the best condition for operation of such bearings, in which we don't have the boundary lubrication, but to get such a hydrodynamic lubrication regime, it is necessary to meet three main conditions. First of all, the sufficient amount of this lubrication should be in the gap. Then the second one is that the speed of rotation of the shaft should be sufficient to generate this pressure in the gap, and the form of the gap should become just to be able to generate such extra pressure. And such bearings works with very small gaps. Could you please the next one? And a couple more. And the most important, maybe the next one. Thank you very much. So the most important characteristics of the plane bearing is the shape of the gap, as well as the middle value of the minimum gap thickness or clearance thickness. And due to the manufacturing tolerances, there is no possibility to manufacture the exact values of the external diameter of the shaft or the internal diameter of the sleeve, because this problem is because of the uncontrollable factors, because of the precision of the manufacturing tools. That's why if we talk about some dimensions, we can't talk about the exact value, but only about the value and some deviations from this value. And in case of the plane bearings, these values are very important, these tolerances, because the smallest height or the smallest value of the gap can be compared with some of the tolerances which are presented here, maybe not so clear as can be seen, but according to the ISO 296 part 1. And this information gives us the ideas to make the result and make the analysis how such deviations in values of inner diameter and outer diameter of the shaft can influence on the pressure distribution in such plane bearing, and as well as the capacity of the bearing as well. Could you please listen the next one? So here is the scheme on which we have the tolerances which arise only because of the accuracy of the shaft manufacturing. And this is enlarged values, but the proportions are kept. It means that here is the value of the minimum gap thickness, and this is can be compared with the area of the tolerances. So the next one, please, and the next. Thank you. So the research of our, the aim of our research was to develop an easy using engineering practice method for prediction the effect of manufacturing tolerances on the pressure distribution and hydrodynamic force value of plane bearings and as well. To get this aim, some of the steps should be made, and the first one is the development of the calculation model. This model takes into account the shaft rotating and the precision rotating of the axis of the shaft in relation to the stationary center of the sleeve. And the next step should be the analysis of pressure distribution in plane bearing gap under these accepted tolerances, and as well as analysis of tolerance influence on fluid film force acting on the general surfaces. So we can just say if this bearing can carry the external load which should be carried by this bearing. And here is the, maybe at once, this is, so as I have already said, the model includes two motion of the shaft. Firstly, the ordinary rotation of the shaft with some frequency, and the axis of the shaft makes the circular trajectory in relation to the center of the stationary sleeve. And of course, if we have deal with fluid flow, so we can't get some information without the basic equation, in this case the Reynolds equation. And under our research, the examined the long plane bearing. That's why the changing in the pressure along the length as well as along the length were neglectable. And this Reynolds equation help us to obtain the pressure distribution as a function of two coordinates. The position of the shaft in clearance and the angle of the axis which goes through the centers of the sleeve and the shaft. So, and these equations express this equation express the equilibrium of viscous fluid located in the gap, because in the most applications the sleeve is stationary, the some of the components of the velocity are equal to 0, and some of them should include, of course, the rotation of the shaft as well as the motion of the axis of the shaft, and some small small vibrations in radial direction. So the next one, please. A couple times. Oh, thank you. So, on the basis of the Reynolds equation solution, the pressure distribution in the gap along the circumferences was obtained, and according to this distribution, if you take a look at the first component and just assume that the second one is equal to 0 in case if there is no vibration in radial direction. So the first component can be close to 0 if the capital omega, which is the frequency of the shaft in relation to the stationary center of the sleeve, is equal to 50% of the natural, is equal to the half of rotation speed of the shaft. So in this case, there is no possibility to generate the pressure, and there is no possibility to curl some loads. And in this can be in practice that this bearing just can bear the necessary load, and they can it can lead to the failure of the machine. So there is the pressure distribution in angular direction in plane bearing for different values of the eccentricity, and as you can see, with the increasing of eccentricity value, this capacity of the bearing increases too. And the maximum, the position of the maximum shifts to the position of the minimum thickness of the gap in a plane bearing. Could you please the next one? And once again, thank you.
The longest one.
Sorry. Well, because the mean value of the gap as well as eccentricity, those two parameters are independent, so we can take the joint probability density function as just a multiplication of the probability function of the mean gap value and the eccentricity. Mostly, and according to the central theory of the theory of probability, if many factors influence on the characteristics, so the law of these characteristics is very close to the normal. So that's why for the mean value of the thickness in the gap of plant bearing, the normal distribution was taken into account. And for the eccentricity, the truncated Rayleigh law was accepted. And on the basis that the small values of this eccentricity as well as the very big values of this eccentricity is equal, has the equal probability, very small probability, because if the shaft center position very close to the center of the sleeve, there is no possibility to have this cone form of the clearance, so we can be able to generate the extra pressure. And when we have a very big value of this eccentricity, so we need to have very viscous lubricant, and it leads in a very big forces of sorry, friction of things. So that's why the probability that this eccentricity is very small and very big is equal to 0. And on the basis of this, we can just get some of the parameters of this truncated Rayleigh law. And using these two probability densities, we can get the probability density for initial position of the angle phi A of the bearing zone. It means this angle from which this extra pressure starts. And it indicates us then how to calculate the force which arises in this bearing. So the next one, please. So it helps us to find the influence of the change in mean clearance value and random eccentricity on the pressure distribution. And here we can see the mean value of pressure along the circumference in plant bearing, and the continuous lines denote the deterministic value. Dotted lines, the value of 10% possible deviation in mean gap value, and dashed lines denote the 20% deviation in mean gap value. And as we can see, they are presented only part of the result, but we can conclude and maybe next one, because here, no, the previous, okay, this one. Here we can see the possible deviation in a pressure which can lead to the bigger values of the force or the smaller values of this hydrodynamic force in plane bearing, and the worst case, then we have these minimum values, because The central brown curve is the deterministic distribution of the pressure. So the smaller they have, the smaller square, it means that they have the smaller force, and it means that if the external load is applied to this bearing, and this bearing can be able to carry this load. So the next one, please. Maybe very briefly here, this what I said before about the force, because I need to just calculate the area under this curve, and this gives me the force components and the conclusions. So please, can be summarized as follows. Under maybe firstly, the tolerances of plane bearings diameters. Here I mean the outer diameter of the shaft and inner diameter of the sleeve have a significant effect on the pressure distribution, as well as hydrodynamic restore force and the position of the beginning and the end of the lubrication wheel. It means there we have this maximum pressure. And the value of the standard deviation of the mean clearance in plane bearing increases, then the value of this force can significantly different, can be significantly different from the calculated one. And according to our calculation, under the standard deviation value of 50% of this mean gap value, the possible deviation of the radial force can differ up to almost 50%. So it means that under some cases, there won't be this bearing won't be able just to carry the load it should carry. And for the further result, it should be taken into account that the hydrodynamic characteristic of the plane bearings are very sensitive to errors in surface shape and the shaft alignment. So that's the most important result that I'd like to present it. Thank you for your attention. And if you have some questions, please feel free to ask.
Thank you very much for your presentation. Thank you once again. We are a little bit out of time, so maybe only one short question from the auditory. Okay, please, Professor.
I don't understand. Once again.
Yeah.
How you calculate rotation speed?
But rotation, I do not calculate the rotation speed. Rotation speed is the initial value that I know under my calculation, because I have the machine which has some range of the rotation speed values. And for this rotation speed, as well for the weight of the parts which are mounted on the shaft, the bearings is selected, and then I can just calculate which, not size, but which the smallest gap is possible, and it leads to the possible force. Thank you for your question.
Okay, do you have any possibility to validate this method? Because these are very interesting analytical methods, but I think this would be quite difficult. Yeah?
I understand, but I think it's possible because there are some results of the failures of the machines, and if find just the information about which geometry of the bearing is used for this machine, so it is possible for me just to validate what I have and what was the reason of this failure, for instance.
So basing on the failures, you will...
If this failure was caused by the not sufficient bearing
lubrication,
yes.
lubrication mode. and the eccentricity, how it was defined? Because it was 0.654.
Yeah,
was it microns, or it was not
not dimensioned. It was the real eccentricity divided by the mean value.
Okay.
Because it's impossible, of course,
Yes,
just if I say about the tolerances and
yes, I would like to correlate it. So that's my question.
No,
okay.
It's impossible.
Thank you once again for your presentation.
Thank you.
And right now we have reached the end of our presentation. This is also the end of the scientific part of the first day. I would like once again thank you very much for your participation and active asking the questions during our presentations. Okay, so now we are closing this part and we will see at the gala dinner. Of course, yes. Goodbye.